Hello there, and welcome to Just About Earth, where curiosity gets cozy and science takes the scenic route toward rest. Tonight, we're drifting into a story so small it almost feels impossible at first. A tale about a plant you could balance on the tip of your finger, yet one that quietly nudged the entire planet into a colder chapter of its long unfolding life. Before we wander too far into ancient oceans and slow-moving climates, let me ask you something gentle and simple. Where are you listening from right now, and what does the world outside your window look like at this very moment? Is it dark and quiet, or bright and busy? Either way, you've arrived here in this small pocket of time, and that feels like a nice place to begin. If you find this kind of slow, thoughtful storytelling soothing, or if it helps your mind ease its grip on the day, you're always welcome to share that calm with others. A like, a subscription, or even a quiet recommendation to someone who might need a peaceful moment can help this little corner of science and rest keep drifting along. Now, let's settle in together, because the story we're about to unfold doesn't start with roaring volcanoes or crashing asteroids. It begins with still water, soft sunlight, and a floating fern that had no idea it was about to change the world. Picture the Earth about 50 million years ago. This was a very different place from the one you know. There were no ice caps at the poles, no vast frozen deserts of snow and wind at the top and bottom of the globe. Instead, the planet was wrapped in warmth. Forests stretched far into what we now call the Arctic. Crocodile-like reptiles basked along riverbanks in regions that today sit beneath layers of ice. The oceans were warmer, the air held more carbon dioxide, and the whole world moved to a slower, softer rhythm of heat and humidity. Up at the very top of the planet, the Arctic Ocean wasn't a churning mass of ice and freezing currents. It was something closer to a quiet, enclosed sea. Continents were arranged differently then. North America and Eurasia leaned closer together, forming a kind of ring around the polar waters. This made the Arctic more isolated, less connected to the wider world of the Atlantic and Pacific. Rivers poured fresh water into it from all sides, diluting the saltiness of the sea and creating a surface layer that was calmer, lighter, and more welcoming to certain kinds of life. Sunlight in the polar regions followed a strange and gentle pattern. Long, bright summers where the sun barely dipped below the horizon were followed by long, dim winters where it barely rose. In this unusual cycle, something small and green found a perfect home. Azolla is a type of tiny floating fern. If you've ever seen a quiet pond covered in a soft green or reddish carpet of plants, you've likely seen a cousin of it. Each individual piece is no bigger than a grain of rice, sometimes even smaller. It drifts on the surface of fresh water, soaking up sunlight and growing at a surprising pace. Under the right conditions, Azolla can double its mass in just a few days, spreading outward until it covers everything it can reach. What makes Azolla especially interesting isn't just its speed or its size. It has a quiet partner living inside its leaves, a type of cyanobacteria that can pull nitrogen out of the air and turn it into a form the plant can use. This little partnership means Azolla doesn't need rich, fertile water to thrive. It can make its own fertilizer, in a way, floating along and growing even when other plants might struggle. Now imagine this tiny fern drifting into the Arctic Ocean of the Eocene epoch, a time when the world was warm and carbon-rich. The surface waters, made fresher by rivers and rain, were calm and stable. Sunlight bathed the region for months at a time. Nutrients flowed in from the surrounding land. For Azolla, this was something like finding an endless open field with perfect weather and no fences. It began to spread. At first, it would have looked like nothing more than patches of green on the water, small clusters moving gently with the currents. But Azolla doesn't grow politely. It grows with enthusiasm. As it multiplied, those patches joined together, forming wider mats. Over time, those mats became something vast, a floating layer of plant life stretching across enormous areas of the Arctic Ocean surface. From above, if you could have looked down from the sky, you might have seen something that resembled a green living skin covering the sea. Beneath that soft surface, the water would have been darker, cooler and quieter, shaded by the fern's endless leaves. While all of this was happening, something else was quietly unfolding in the background. Every green leaf of Azolla was doing what plants do best. It was pulling carbon dioxide out of the air and using sunlight to turn it into its own body. This process, photosynthesis, is one of the most powerful chemical tricks on Earth. It takes an invisible gas from the atmosphere and locks it into solid living matter. As Azolla grew and spread, it was slowly, steadily drawing down carbon from the sky. Not in a dramatic, sudden way, but in a patient, persistent one. Each tiny plant was like a small green hand reaching up and taking a breath of carbon dioxide over and over again, day after day, season after season. Normally, when plants die, that carbon doesn't stay locked away forever. Leaves fall, plants decay, and microbes break them down, releasing much of that carbon back into the air or water. It's part of a cycle, a long exchange between life and the atmosphere. But the Arctic Ocean of this ancient world had a special feature. Below the fresh, light surface layer was heavier, saltier water that didn't mix very well with what was above it. This created a kind of barrier. When Azolla plants died, many of them sank past the surface layer and settled into the deeper, darker parts of the sea. Down there, conditions were different. There was less oxygen, fewer organisms to break the plants down completely. Instead of being fully recycled, a significant portion of that plant material was buried in the mud on the ocean floor. The carbon inside it stayed there, locked away in sediments, out of reach of the atmosphere. This is where the story starts to feel almost like a slow planetary breath being held. Over thousands of years, then tens of thousands, then hundreds of thousands, this process continued. Azolla grew, captured carbon, died, and sank. Again and again. Layer upon layer of plant material built up in the sediments beneath the Arctic waters. With each cycle, a little more carbon was removed from the air above the planet. Carbon dioxide is one of the main gases that helps trap heat in Earth's atmosphere. When there is more of it, the planet tends to be warmer. When there is less, the planet can cool. The changes Azolla was making weren't dramatic on a human timescale. No one would have noticed a colder winter or a cooler summer from one generation to the next. But on a geological timescale, the effect was steady and relentless. The atmosphere began to change. As carbon levels slowly dropped, the balance of heat on Earth shifted. Temperatures, especially near the poles, started to ease downward. The warm, almost tropical conditions of the Arctic began to soften into something milder. Forests that once thrived near the top of the world started to retreat. The planet, which had been in a long warm phase, began to edge toward a cooler one. It's important to pause here and take in how unusual this is. We often think of climate change as something driven by massive forces, volcanoes releasing clouds of gas, continents drifting and redirecting ocean currents, asteroids slamming into the planet. All of those things have shaped Earth's history, but here, in this quiet corner of deep time, a tiny floating plant played a role in shifting the global thermostat. Not by force, not by violence, just by growing. The Azolla Event, as scientists now call it, wasn't a single moment. It was a long chapter in Earth's story, stretching over perhaps 1 million years or more. During that time, the Arctic Ocean may have been covered again and again with these green mats, each one part of a slow, cumulative change. How do we know any of this happened? After all, no one was there to watch ancient ferns spread across polar seas. The answer lies deep beneath the modern Arctic Ocean, in long narrow cylinders of mud and rock pulled up from the seafloor by research ships. These sediment cores are like time capsules. Each layer represents a different period, a different set of conditions, a different moment in Earth's past. When scientists examined cores taken from Arctic sediments, they found something unexpected. Thick layers rich in organic material, packed with the fossilized remains of freshwater plants. Mixed in with this plant matter were chemical signatures that pointed directly to Azolla and its bacterial partners. It was as if a long-lost green world had left its fingerprint in the mud. These layers told a story of repeated blooms, of surface waters fresh enough for Azolla to thrive, and of deep waters quiet enough to bury it without fully breaking it down. The evidence lined up with models of how the Arctic Ocean was structured at the time, and with signs of a gradual drop in atmospheric carbon dioxide during the same period. Piece by piece, a picture formed. A small plant growing in the right place at the right time had become part of a global system that shifted the planet's climate. If you think about it in a more familiar way, it's a bit like filling a bathtub with the faucet barely open. At first, nothing seems to happen. The water level looks the same. But if you leave it long enough, eventually the tub fills. Azolla's influence was like that slow, quiet stream, adding up over immense spans of time. As the world cooled, other changes followed. Ice, which had been mostly absent from the poles, began to appear more regularly. The great ice sheets that would later define the modern Arctic and Antarctic were still far in the future, but the trend had begun. Ocean currents shifted, weather patterns adjusted, life on land and in the sea adapted to a planet that was no longer quite as warm as it had been. All of this from a plant that most people today would barely notice if it floated past them in a pond. There's something quietly humbling about that. It suggests that the Earth's systems are deeply interconnected, that small things, given enough time and the right conditions, can become part of much larger stories. As you're listening to this, wherever you are, your own world is full of tiny processes unfolding all the time. Leaves turning sunlight into sugar, microbes in the soil breaking down fallen branches, the slow movement of carbon, water, and energy through air, land, and sea. Most of it happens far below the level of everyday attention, but over long stretches of time, it shapes the planet you walk on. The Azolla Event isn't just a tale about the past. It's also a reminder of how sensitive Earth's climate can be to changes in the balance of carbon. In that ancient world, a natural process slowly drew carbon out of the atmosphere and cooled the planet. Today, human activity is doing the opposite, adding carbon back into the air at a pace far faster than most natural systems can counter. But for now, let's stay with the quiet, floating fern and its ancient sea. Imagine standing on the shore of that Eocene Arctic, if such a thing were possible. The air would feel mild, perhaps even warm. The light in summer would stretch on and on, casting long reflections across a surface that looked less like open water and more like a vast living field. Birds might circle overhead. Insects would skim the green surface. Beneath it all, the slow rain of dead plants would drift down into the depths, layer by layer, building a hidden archive of carbon and time. This wasn't a dramatic moment. There were no sudden freezes, no instant shifts from warmth to ice. Just a gradual turning of a very large dial, guided by countless, almost invisible acts of growth and decay. Long before ice became the defining feature of the far north, the top of the world was a place of softness rather than sharpness, of water and forest rather than snow and stone. If you could drift back through time, past the familiar outlines of continents, and into a version of Earth that feels almost like a different planet, you would arrive at a moment when the Arctic was not a crown of white, but a basin of blue and green, wrapped in warmth and quiet. The planet itself was in a state scientists often call a greenhouse world. This doesn't mean there were literal greenhouses scattered across the landscape, of course, but it does describe a global atmosphere that held onto heat more effectively than it does today. Carbon dioxide levels in the air were significantly higher. The oceans were warmer not just at the surface, but deep down as well. There was less of a sharp contrast between the tropics and the poles, so the entire planet felt more evenly tempered, like a room where the heater had been left on just a little too long. At the top of this world, the Arctic Ocean sat in a kind of sheltered bowl. The continents were arranged in a way that almost cradled it. North America leaned toward Europe and Asia, leaving only narrow passages connecting the polar waters to the wider, more restless oceans beyond. This made the Arctic less like an open highway for currents, and more like a quiet bay where water could linger, mix slowly, and settle into gentle layers. Rivers from the surrounding land poured into this basin, carrying fresh water from rainfall, melting snow in distant mountains, and the slow seep of groundwater through ancient soils. Over time, this fresh water formed a lighter layer at the surface of the Arctic Ocean. Beneath it, heavier, saltier water sat lower down, creating a kind of invisible boundary between the two. The result was a surface that was calmer and more stable than what you would find in most parts of the sea. If you stood at the edge of this ancient Arctic and looked out, you might not have seen the restless, wave-tossed horizon we often associate with polar waters today. Instead, the surface could appear almost lake-like at times, especially during the long, bright months when the sun barely left the sky. Light would spread across it in a soft, unbroken way, reflecting off water that held fewer storms and fewer sudden shifts. The land around this ocean would have felt just as surprising. Instead of tundra and ice, there were forests. Trees that today you would expect to find much farther south grew near the polar circle. Some of them were broad-leaved, shedding foliage in a seasonal rhythm. Others were more like the conifers you might recognise, but taller, thicker, and surrounded by a richness of plant life that doesn't usually pair with the idea of the far north. Animals moved through these forests and along the river banks. Early relatives of modern mammals wandered among the trees. Birds took advantage of the long summer days to feed and nest. In the water, fish and plankton formed the base of a food web that thrived in the warmth and the steady supply of nutrients flowing in from the land. All of this was happening under a sky that held more heat than it does now. Carbon dioxide, along with other greenhouse gases, trapped a portion of the sun's energy as it radiated back towards space. The effect wasn't dramatic in the sense of day-to-day extremes, but it shaped the long-term average, nudging global temperatures upward and keeping ice at bay. What's interesting is that this warmth didn't mean the planet was chaotic or unstable. In many ways, it was a steady, balanced system, just tuned to a different setting. The Earth has spent much of its history in states that would feel unfamiliar to us today. Ice-covered poles like the ones we know now are actually the exception, rather than the rule in the deep timeline of the planet. The Arctic's quiet nature during this time had consequences that reached far beyond its own shoreline. Because it was more isolated from the global ocean, changes that happened there could linger rather than being quickly swept away. Water temperatures, salinity, and chemical composition could build their own patterns, shaped by local conditions and the steady input of rivers and rainfall. The surface layer of fresh water was especially important. Being lighter, it tended to stay on top, resisting mixing with the denser salt water below. This created a kind of gentle stratification, like layers in a carefully poured drink. The top layer, warmed by the sun and enriched by nutrients from the land, became a welcoming environment for life that preferred calmer, less salty conditions. Sunlight in the Arctic followed its own strange rhythm. During summer, the sun circled the sky without truly setting, bathing the region in a long, continuous glow. During winter, it dipped below the horizon for extended periods, leaving the world in a softer, dimmer state. For plants and microorganisms, this created a pattern of intense growth, followed by quieter, slower phases. In most parts of the ocean, strong currents and frequent storms can disrupt surface layers, mixing water from top to bottom and back again. But in this ancient Arctic, the sheltered geography and the steady freshwater input made such mixing less common. The surface could remain stable for long stretches of time, allowing anything that thrived there to spread without being constantly scattered or sunk. This stability was not something you could see directly, but it was something life could feel. Floating plants, microscopic algae, and other surface-dwelling organisms benefited from an environment where they weren't regularly plunged into deeper, darker waters. They could stay in the light, soaking up energy and growing outward instead of being pulled down. The warmth of the period also meant that the growing season was generous. Even in the polar regions, temperatures during summer could support active plant growth. Combined with the long hours of daylight, this created conditions that were unusually productive for such a high latitude. It's worth taking a moment to reflect on how different this is from the Arctic you might picture today. Modern polar waters are often cold, turbulent, and covered in ice for much of the year. The light conditions are still extreme, but the temperatures and the chemistry of the water tell a very different story. In the ancient greenhouse world, the Arctic was more like a calm, high-latitude lake connected to the ocean rather than a frozen frontier. The surrounding continents also played their part in shaping this environment. Their positions influenced wind patterns, rainfall, and the routes rivers took to reach the sea. These rivers didn't just bring fresh water, they carried minerals and nutrients eroded from rocks and soils. Over long periods, this steady flow enriched the surface waters, providing the raw materials needed for plant growth. As these nutrients entered the Arctic basin, they tended to remain there rather than being quickly flushed out to the wider ocean. This meant the region could gradually build up a kind of natural fertility, a quiet abundance that wasn't immediately obvious, but was deeply important for what would come next. Below the surface, the deeper waters moved more slowly. Without strong mixing, oxygen from the air had a harder time reaching the depths. This created zones where the water was lower in oxygen, especially near the seafloor. These conditions would later become crucial for what happened to the remains of plants and organisms that sank out of the surface layer. From a distance, the planet during this time might have looked peaceful and balanced. There were no signs of an impending shift. The warmth had persisted for millions of years. The forests had adapted to it. The oceans had settled into their patterns. Everything seemed, in a broad sense, comfortable. But Earth's systems are rarely static, even when they appear stable. Small changes can accumulate, interactions can build upon each other, and new feedback loops can emerge. The quiet Arctic, with its calm surface and layered waters, was setting the stage for something that didn't need violence or sudden disruption to leave its mark. Think of it like a long, slow inhale. The atmosphere, rich in carbon dioxide, was part of a balance between the air, the land, and the sea. Plants on land and in water were constantly exchanging gases with the sky. Some carbon was being buried in soils and sediments. Some was being released through decay and volcanic activity. Over time, these processes kept the system in a rough equilibrium. What made this period special was the way the Arctic's geography and climate allowed that balance to be nudged in a particular direction. The calm surface waters, the steady supply of nutrients, and the long days of sunlight created a niche that favoured certain kinds of life. And when those organisms grew, they didn't just become part of the food web, they became part of the planet's chemistry. As you imagine this world, try not to think of it as a single snapshot. It's more like a long, slowly changing scene. Over centuries and millennia, rivers shifted their courses. Forests expanded and retreated. Ocean currents adjusted to subtle changes in continental position and sea level. The atmosphere responded to volcanic eruptions, weathering of rocks, and the steady work of living things. Through all of this, the Arctic remained a kind of quiet corner, a place where changes could accumulate gently rather than being swept away. The surface waters continued to receive fresh water and sunlight. The deeper layers remained darker and lower in oxygen. The sediments at the bottom slowly built up, layer by layer, like pages in a book that no one would read for millions of years. This layered structure of the Arctic Ocean wasn't unique in the world, but its scale and persistence were unusual. It was large enough and stable enough to host processes that, over time, could influence the planet beyond its own boundaries. From a human perspective, it's easy to overlook places that seem calm and uneventful. We tend to focus on dramatic landscapes and sudden changes. But in Earth's story, some of the most powerful shifts have come from environments that change very slowly and very quietly. The warmth of this period also had a subtle effect on the chemistry of the oceans. Warmer water holds less dissolved gas than colder water. This means that as temperatures rose, the oceans were slightly less able to store carbon dioxide in dissolved form. More of it remained in the atmosphere, reinforcing the greenhouse conditions. It was another piece of a system that had settled into a warm mode. At the same time, warmer temperatures increased rates of chemical weathering on land. Rainfall and heat helped break down rocks, releasing minerals that rivers carried to the sea. These minerals, in turn, supported the growth of marine organisms that used carbon to build shells and skeletons, which could then sink and become part of the sediment. All of these processes were interconnected, forming a network of slow exchanges between air, water, and stone. The Arctic, with its unique geography and climate, became one of the quieter hubs in that network, a place where certain pathways were favoured over others. If you were to drift along the surface of that ancient polar sea, you might have noticed how little disturbance there was compared to more open waters. The wind could still raise ripples and waves, of course, but the overall feel would have been gentler. The light would reflect off the surface in long, soft streaks. The air might carry the scent of nearby forests rather than the sharp tang of ice. Beneath you, the water would be layered, each stratum with its own temperature, salinity, and chemistry. Tiny organisms would move through the upper layer, feeding on sunlight and nutrients. Particles of organic matter would slowly fall through the boundary into the deeper, darker zone, beginning a long journey toward the seafloor. This slow rain of material was constant, but it wasn't yet extraordinary. It was simply part of how oceans work. What made the difference was how much of that material could be produced at the surface, and how much of it could escape being fully broken down before it reached the bottom. The warmth of the planet and the calmness of the Arctic surface were both essential ingredients in what would follow. Without the heat, the growing season would have been shorter. Without the stability, surface-dwelling plants and microorganisms would have had a harder time establishing wide, continuous populations. In this way, the quiet Arctic wasn't just a backdrop, it was an active participant in the story, shaping the conditions that allowed something small to become something influential. If you were to lean over the edge of that ancient calm Arctic sea and scoop up a handful of the water, you might not notice anything extraordinary at first. The surface would feel cool and smooth against your skin. Light would scatter across it in soft reflections. But if you let the water settle in your palm for a moment, tiny green flecks would begin to gather, drifting together as if drawn by an invisible thread. Those little pieces, no bigger than a grain of rice and sometimes smaller than a pinhead, were Azolla. It doesn't look like much. Even today, when you find it floating in a quiet pond or a slow-moving stream, it's easy to mistake it for a smudge of algae or a bit of duckweed. Each individual plant is made of small, overlapping leaves arranged along a delicate stem, forming a shape that's part fern, part feather, part something entirely its own. The leaves are often a soft green, though in bright light or cooler temperatures, they can blush into shades of red or bronze like they're quietly showing off. What makes Azolla special isn't its appearance, it's what it does and how it does it. Azolla belongs to a small group of ferns that have decided life is better on the surface of the water, rather than rooted in soil. Instead of digging into the ground, it floats freely, supported by tiny air pockets in its leaves. This gives it access to sunlight without the competition faced by plants growing on land or below the surface. It's like having a front row seat to the sun, all day, every day. But even that advantage wouldn't be enough to turn a tiny plant into a global player. The real secret lies hidden inside its leaves. Tucked within the structure of each Azolla plant is a microscopic partner, a type of cyanobacteria often referred to as a blue-green alga, though it's actually a kind of bacterium. This partner has a remarkable ability. It can take nitrogen gas from the air, which most plants can't use, and convert it into a form that plants can absorb and turn into proteins and other essential compounds. In most ecosystems, nitrogen is a limiting resource. Plants compete for it in the soil or water, and their growth is often held back by how much of it they can access. Azolla, thanks to its bacterial companion, doesn't have to wait for nitrogen to be delivered by runoff or decay. It carries its own tiny factory, quietly producing fertilizer inside its leaves. This partnership turns Azolla into a kind of self-sufficient floating farm. Given enough sunlight and a bit of phosphorus and other trace nutrients from the water, it can grow at a pace that feels almost unreal for something so small. Under the right conditions, Azolla can double its mass in a matter of days. A few scattered plants can become a continuous mat in a surprisingly short time. The surface of a pond or a slow river can go from open water to a green carpet that looks like it was rolled out overnight. Now take that ability and place it in the ancient Arctic setting we just explored. A calm, stable surface layer of fresh water. Long hours of sunlight during the summer months. A steady supply of nutrients flowing in from surrounding land. For Azolla, it was like stepping into a world designed specifically for it to thrive. At first, its arrival in the Arctic Ocean would have been subtle. A few plants drifting in from rivers or coastal wetlands, maybe carried by currents, maybe transported on the feet of birds moving between bodies of water. They would have floated along, growing slowly, testing the conditions. The surface waters, being fresher and lighter than the saltier depths below, offered a gentle place to settle. The lack of strong mixing meant these small plants weren't constantly being pushed down into darker, less hospitable layers. They could stay where the light was and where their tiny bacterial partners could continue their quiet work. Once Azolla found this niche, it didn't just survive, it flourished. Imagine watching from above as patches of green begin to spread across the surface. At first, they're isolated islands, drifting apart and coming back together with the slow movement of the water. Over time, these islands start to connect. Thin lines of plants bridge the gaps. What were once separate patches become larger fields. As these fields expand, they start to change the environment around them. The water beneath the mat receives less direct sunlight, becoming cooler and darker. The surface itself becomes more stable, dampening small waves and reducing evaporation. It's a subtle feedback loop, but one that favours the continued presence of the plants. Azolla isn't just growing in the environment, it's shaping it. On a microscopic level, each leaf is a busy little workshop. Sunlight pours in, driving the process of photosynthesis. Carbon dioxide from the air dissolves into the thin layer of water on the leaf's surface, then diffuses into the plant cells. There, it's combined with water to form sugars, the building blocks of the plant's body. At the same time, inside specialized cavities in the leaves, the cyanobacteria are pulling nitrogen from the air. This nitrogen is turned into ammonia and other compounds that Azolla can use to build proteins and grow new tissue. The plant in return provides the bacteria with a safe home and a steady supply of sugars from photosynthesis. It's a quiet exchange, happening billions of times across the surface of the Arctic Ocean. Each individual partnership is small. Together, they form a vast living system that is constantly drawing material from the air and turning it into plant matter. From a distance, the mats of Azolla might have looked almost peaceful, like a soft floating meadow. But beneath that calm appearance was an engine of growth and chemical transformation. As the plants aged, older leaves and stems would break off or die. Some of this material would be consumed by small organisms living on or near the surface. Insects, tiny crustaceans and microorganisms would feed on the decaying plant matter, becoming part of a simple food web. But a significant portion of the dead Azolla didn't stay at the surface. It sank. The plant material, heavier than water once it lost its air-filled structure, would drift down through the boundary between the fresh surface layer and the saltier depths below. This boundary, called a halocline, acted like a kind of invisible gate. Once the plant matter passed through it, it entered a world with less oxygen and fewer organisms capable of breaking it down completely. The deeper waters of the Arctic basin were quieter and darker. Decomposition still happened there, but more slowly. Some of the carbon locked inside the plant tissue was released back into the water. Some was transformed by microbes. But a meaningful fraction of it remained intact long enough to settle onto the seafloor. There it joined layer upon layer of other sinking material, building up sediments rich in organic carbon. Over time, these layers were buried by more mud and debris, pressing them deeper into the Earth's crust and isolating their carbon from the atmosphere above. This is the part of the story where Azolla's role becomes truly planetary. Every leaf that grew pulled a bit of carbon dioxide out of the air. Every leaf that sank and was buried took some of that carbon with it, locking it away for thousands, then millions of years. The process didn't need to be fast to be effective, it just needed to be persistent. Picture a vast, slow-moving conveyor belt. At one end, carbon is taken from the atmosphere and turned into plant matter. At the other, that plant matter is buried in sediment. The belt moves quietly, steadily, day after day, year after year. Over long spans of time, the atmosphere feels the difference. Carbon dioxide levels begin to drop, not suddenly, but enough to shift the balance of heat trapped around the planet. The greenhouse world starts to cool, almost imperceptibly at first. Temperatures near the poles ease downward. The contrast between equator and pole grows a little sharper. Azolla, of course, isn't aware of any of this. It's just growing, floating, and sinking, following the simple rules of its biology. But in doing so, it becomes part of a much larger system, one that links the smallest leaves to the largest climate patterns. What's striking about this story is how indirect the connection is. There's no single moment you can point to and say, this is when the planet began to change. Instead, there's a long accumulation of small actions. A leaf grows, a leaf sinks, a layer of sediment thickens. The air above holds a little less carbon than it did before. It's the kind of change that only becomes obvious when you step back and look across immense spans of time. From a scientific perspective, this makes the Azolla Event both fascinating and challenging to study. Researchers can't rely on a single clue. They have to piece together evidence from many sources. Sediment cores from the Arctic seafloor reveal layers rich in organic material, often with chemical markers that point to freshwater plants and their bacterial partners. Fossil pollen and spores give hints about what was growing on nearby land, helping to reconstruct the broader environment. Isotopes of carbon in rocks and shells record changes in the global carbon cycle, showing when carbon was being removed from the atmosphere more rapidly. Climate models are used to test whether the amount of carbon Azolla could realistically have buried is enough to explain the cooling seen in other records. These models take into account growth rates, surface area coverage, rates of decomposition, and how quickly sediments can trap carbon in a way that keeps it from returning to the air. The picture that emerges isn't perfectly sharp, but it's compelling. It suggests that for a significant period, Azolla blooms covered large portions of the Arctic Ocean, that these blooms persisted long enough and were buried efficiently enough to make a noticeable dent in atmospheric carbon levels. It's worth remembering that Azolla wasn't acting alone. Other processes were also influencing the climate at the time. Continental drift continued to reshape ocean currents. Volcanic activity released and removed gases from the atmosphere. Weathering of rocks on land pulled carbon dioxide out of the air in its own slow way. The story isn't about a single hero changing the world by itself. It's about how a small, simple organism became part of a network of forces that, together, nudged the planet in a new direction. Still, there's something appealing about focusing on Azolla. It gives a face, or at least a leaf, to a process that might otherwise feel abstract. It turns the idea of carbon cycles and climate feedbacks into a more tangible image. A floating fern, quietly breathing in carbon and drifting down into the dark. If you were to hold a piece of Azolla in your hand today, it would feel light and fragile. It wouldn't seem capable of doing much at all. but its ancestors, multiplied across a polar sea, were part of a story that reached from the surface of the water to the temperature of the entire planet. There's also a deeper lesson woven into this. Earth's history isn't just shaped by the biggest and most dramatic events, it's shaped by persistence, by processes that operate slowly, steadily, and almost invisibly. Rivers don't carve canyons in a day. They do it by flowing endlessly, grain by grain. Coral reefs aren't built by single storms, but by countless tiny organisms laying down skeletons over generations. In the same way, Azolla didn't change the climate with a single bloom. It did it by growing, sinking, and being buried, over and over again. As the Arctic world of the Eocene continued to evolve, the presence of these floating mats would have had local effects as well. By shading the water, they could alter temperature and light conditions for other organisms. By changing the chemistry of the surface layer, they could influence which species of plankton thrived and which struggled. These local shifts would feed back into the larger system. Different plankton communities can affect how much carbon sinks to the sea floor. Changes in water temperature and mixing can influence how gases move between ocean and atmosphere. The story becomes less about a single plant, and more about a web of interactions all linked together. From a human point of view, it's tempting to look for simple cause and effect relationships. Azolla appears, the planet cools. But the reality is more nuanced. The fern was one thread in a much larger tapestry. Pulling on that thread influenced the pattern, but it didn't create the entire design on its own. Still, without that thread, the pattern might have looked very different. As you picture this ancient scene, try to hold both scales in mind at once. On the small scale, a tiny plant floating on the surface of the water, its leaves no bigger than a fingernail, its life measured in days or weeks. On the large scale, a planet slowly adjusting its temperature over millions of years, ice beginning to appear where there was once only forest and sea. Somewhere between those two scales is the story we're following. It's a reminder that Earth's systems don't respect the boundaries we often draw between small and big. A leaf can be part of a climate pattern, a bacterium can influence an atmosphere. Long before the Arctic became a place most people imagine as distant and inhospitable, it was something closer to a quiet meeting point between land, water, and sky. The top of the world was not defined by ice and silence, but by slow rivers, gentle seas, and a landscape that felt in many ways welcoming to life that could take advantage of stillness and light. This is where floating ferns like Azolla didn't just arrive by chance. They found a home. To understand how a tiny freshwater plant managed to settle in a region we now associate with saltwater and frozen horizons, it helps to step back and look at the shape of the world itself during that period. The continents were arranged in a way that gave the Arctic a very different character. Instead of being an open gateway between major oceans, it was more like a broad basin, partially enclosed by the land masses of North America, Europe, and Asia. Narrow connections linked it to the wider seas, but those connections were shallow and limited, restricting the free exchange of water. This geography mattered in ways that aren't immediately obvious. Oceans are not just big, uniform bodies of water. They're constantly moving, mixing, and sorting themselves by temperature and saltiness. In most places, dense, salty water can sink and spread, while lighter, fresher water stays near the surface. Strong currents and storms can stir these layers together, creating a dynamic, restless environment. In the ancient Arctic, that stirring was gentler. Rivers flowing from the surrounding continents poured vast amounts of fresh water into the polar basin. This wasn't a trickle. Over long stretches of time, these rivers delivered a steady, reliable supply of rainwater and melted snow from far inland. That fresh water spread across the surface of the Arctic Ocean, forming a lighter layer that floated on top of the saltier, heavier water below. The result was a kind of natural lid. The surface layer resisted mixing with the depths beneath it. Even when winds blew across the sea, they mostly ruffled the top without fully churning the whole water column. This created a stable, predictable environment right at the surface, the exact place where floating plants like Azolla prefer to live. But water chemistry alone doesn't explain how these ferns got there in the first place. Azolla doesn't swim, it doesn't travel on its own, it drifts. So its journey to the top of the world would have depended on other forces, both gentle and persistent. One likely route was through the network of rivers and wetlands that surrounded the Arctic basin. Azolla thrives in slow-moving freshwater environments. Streams, floodplains, marshes and shallow lakes provide the kind of calm conditions it needs to grow and spread. As these rivers made their way toward the sea, they would have carried small fragments of plant life with them. A few leaves, a small cluster of stems, a bit of green caught in the flow. When those fragments reached the surface waters of the Arctic Ocean, they would have encountered something unusual for a marine environment. Instead of immediately being exposed to salty conditions that could stress or kill them, they would have found a surface layer that was relatively fresh. Not identical to river water, but fresh enough to be tolerable, especially for a plant that could adapt and grow quickly. Birds may have played a role as well. Even in ancient times, birds moved between bodies of water, feeding, resting, and nesting along migration routes. Azolla is light and sticky enough that small pieces can cling to feathers or feet. A bird landing in a pond covered in ferns and then flying to another wetland could unintentionally carry the plant with it. Over generations, these small acts of transport could spread Azolla across wide regions. Once a few plants reached the Arctic surface waters and survived, the real work began. The long summer days of the polar region offered something that many lower latitude environments could not: continuous sunlight. For weeks and months at a time, the sun hovered above the horizon, circling the sky without fully setting. For a plant that runs on photosynthesis, this was like an extended work shift with no closing time. Azolla could soak up light almost constantly during these periods, driving its growth at a pace that would have been hard to match elsewhere. Its bacterial partners inside the leaves kept supplying it with nitrogen, removing another common limitation on plant growth. As long as there was enough phosphorus and a few other nutrients in the water, the fern could keep expanding. Those nutrients arrived once again, courtesy of the land. The same rivers that delivered fresh water also carried dissolved minerals and particles of soil. Rain and weathering broke down rocks across the continents, releasing phosphorus, iron and other elements into the runoff. When that runoff reached the Arctic basin, it didn't immediately flush out to the wider ocean. Instead, much of it lingered in the surface layer. Over time, this created a nutrient-rich environment, a kind of floating pantry for surface-dwelling organisms. Algae, plankton and Azolla itself all benefited from this steady supply. But Azolla had an edge. Its ability to fix its own nitrogen meant it could take advantage of nutrients that other plants couldn't fully use on their own. As small patches of Azolla grew, they began to interact with the physical environment in subtle ways. The mats of plants dampened surface waves, reducing the mixing of water at the top. This made the surface layer even more stable, which in turn favoured the continued presence of floating plants. It was a gentle feedback loop. Stability encouraged growth. Growth increased stability. Temperature played a role as well. The greenhouse climate of the time meant that even at high latitudes, surface waters during summer were warm enough to support active plant metabolism. Cold can slow down the chemical processes inside cells, but warmth keeps them moving. In this ancient Arctic, Azolla could grow efficiently for long stretches of the year. During the darker winter months, growth would have slowed. The sun dipped below the horizon for extended periods, and photosynthesis would have been limited. Some of the fern would die back. Some would survive in sheltered areas or in a dormant state. When the light returned, the survivors could spread again, seeding the next season's growth. This cycle of expansion and contraction likely repeated year after year, with the overall trend moving toward wider and more persistent coverage, as long as conditions remained favourable. One of the most interesting aspects of Azolla's presence in the Arctic is how it blurs the line between freshwater and marine environments. Today, we tend to think of these as very different worlds, each with its own distinct set of plants and animals. But the ancient Arctic surface layer was something in between. Not fully freshwater, not fully marine. This in-between state created a niche that few other places on Earth offered. For Azolla, it was close enough to freshwater to survive, but large and open enough to allow it to spread across vast areas. Instead of being confined to ponds and rivers, it had access to an entire sea. As the mats grew, they would have influenced more than just the water directly beneath them. The plants absorbed sunlight, shading the surface and reducing the amount of light that penetrated into the water column. This could limit the growth of certain types of algae and plankton below, changing the composition of the microscopic community in the water. The ferns also affected the exchange of gases between the ocean and the atmosphere. A dense mat of plants at the surface can act like a partial barrier, slowing the movement of carbon dioxide and oxygen in and out of the water. This could alter local concentrations of these gases, further influencing biological and chemical processes in the surface layer. Over long periods, these small local effects added up to broader patterns. Areas with persistent Azolla coverage would develop different water chemistry and biological communities than areas without it. These differences could in turn influence how much organic material sank to the seafloor and how efficiently carbon was buried in sediments. The top of the world, in this sense, became a patchwork of micro-environments. Some regions might have been dominated by floating ferns. Others might have remained more open, with different types of plankton at the surface. Currents, even gentle ones, would have slowly shifted these patches around, creating a moving mosaic across the Arctic basin. From the perspective of the fern itself, none of this mattered. It responded to light, nutrients, and temperature. It grew where it could and faded where it couldn't. But from the perspective of the planet, these patterns influenced the flow of carbon and energy through the system. There's also a geological side to this story that often gets overlooked. The shape of the seafloor beneath the Arctic Ocean affected how water moved and where sediments accumulated. Shallow shelves near the edges of the basin provided areas where sinking plant material could be quickly buried by other sediments. Deeper central regions might have collected organic-rich muds more slowly, building thick layers over time. These physical features created zones where carbon burial was more or less efficient. Areas with high burial rates became long-term storage sites for the carbon that Azolla and other organisms pulled from the atmosphere. Areas with lower burial rates allowed more of that carbon to be recycled back into the water and air. The distribution of these zones influenced how effective the entire system was at reducing atmospheric carbon levels. It wasn't just about how much Azolla grew, it was also about where its remains ended up. In this way, the fern's home at the top of the world wasn't just defined by surface conditions, it extended all the way down to the shape and chemistry of the seafloor. As scientists try to reconstruct this ancient environment, they rely on a mix of clues. Sediment cores show layers rich in organic material, often with chemical signatures that point to freshwater plants. Fossil remains of pollen and spores reveal what was growing on nearby land. Isotopic ratios in minerals tell stories about water temperature, salinity, and the movement of carbon through the system. Computer models help tie these pieces together, simulating how water might have flowed, how surface layers could have formed, and how plants like Azolla might have spread under different conditions. By adjusting variables like river input, continental positions, and atmospheric carbon levels, researchers can test which scenarios produce patterns that match what they find in the rocks. What emerges from this work is a picture of the Arctic not as a passive backdrop, but as an active, dynamic environment. Its geography, climate, and biology all interacted to create a space where a floating fern could do something extraordinary. There's a certain quiet poetry in that idea, even if we're trying to avoid getting too poetic about it. A place defined by stillness and light becoming a hub of slow, powerful change. it also highlights how sensitive Earth systems can be to the details of place. If the continents had been arranged differently, if the connections to the wider oceans had been broader or deeper, the Arctic surface layer might not have remained fresh and stable. Stronger currents could have mixed the water more thoroughly, disrupting the calm conditions Azolla needed. If river input had been lower, the surface might have been saltier, less welcoming to a freshwater plant. If the climate had been cooler, the growing season might have been too short to allow widespread blooms. The fern's success depended on a specific combination of factors: geography, climate, biology, and chemistry, all lined up in a way that doesn't happen often in Earth's history. This is one of the reasons the Azolla Event stands out to scientists. It's not just an example of a plant influencing climate, it's an example of how rare alignments in Earth systems can create unique pathways for change. As you imagine this ancient Arctic, try to hold on to the idea of it as a place of opportunity rather than extremes. A place where light lingered, water rested in gentle layers, and nutrients drifted in from distant lands. In that setting, a tiny plant found not just a place to survive, but a place to spread, to persist, and to become part of something far larger than itself. At the top of the world, where the sky seemed to stretch wider than anywhere else, and the horizon curved gently around a quiet enclosed sea, 3 simple ingredients came together in a way that rarely happens on a planetary scale. Light, water, and time aligned, not in a dramatic collision, but in a slow, steady arrangement that allowed something small and green to multiply beyond anything its size would normally suggest. Sunlight was the first and perhaps the most obvious part of this story. The polar regions follow a rhythm unlike anywhere else on Earth. For months during the summer, the sun doesn't truly set. It dips low, skimming the edge of the sky, casting long shadows and soft gold reflections across the water, but it never disappears completely. This creates a day that seems to stretch on without an end, a continuous window of light that plants can use almost without interruption. For a floating fern like Azolla, this was an extraordinary gift. Most plants, even those in the tropics, experience a regular cycle of light and darkness. They grow during the day and rest at night. Their internal systems are tuned to that rhythm. In the ancient Arctic summer, Azolla could keep working around the clock, absorbing energy hour after hour, leaf after leaf. Photosynthesis is not a fast process in the way we usually think of speed. It's a chain of chemical steps, each one taking a bit of time. More light doesn't mean infinite growth, but it does mean that the system can keep running at its upper limit for longer stretches. In a place where the sun barely left the sky, Azolla could maintain high levels of activity for weeks on end, building new tissue almost continuously. Freshwater was the second piece, and in some ways the more subtle one. The Arctic Ocean of that era was not uniformly salty from top to bottom. The steady input of rivers created a surface layer that was lighter and less dense than the water below. This layer floated quite literally on top of the deeper, saltier sea. For a freshwater plant, this meant the difference between survival and stress. Salt can interfere with the way plant cells manage water and nutrients. Too much of it can damage tissues and slow growth. The fresher surface layer provided Azolla with an environment that was close enough to its natural habitat to allow it to thrive. This layer also acted like a cushion. It absorbed much of the energy from wind and small storms, preventing the deeper waters from being mixed upward too often. As a result, the surface remained relatively calm. Floating plants weren't constantly being dragged down into darker, less favourable conditions. They could stay where the light and air were. The third ingredient, time, is easy to overlook because it doesn't leave a visible mark in the same way light and water do, but time is what allowed the effects of the first two to accumulate. Azolla didn't cover the Arctic Ocean in a single season. It didn't appear as a sudden, dramatic blanket of green. It spread gradually, a patch here, a patch there, a wider mat one year, a thinner one the next. Over generations, those patches overlapped, merged, and extended farther from their original sources. Each summer, the long days allowed the fern to grow rapidly. Each winter, some of it died back. But enough survived in sheltered areas, or in the form of spores and fragments to begin again when the light returned. Over many cycles, the overall trend leaned toward expansion rather than retreat. It's worth pausing to think about how unusual this combination of conditions really is. Most of the world's oceans are too salty for freshwater plants. Most freshwater bodies are too small to allow something like Azolla to spread across thousands of square kilometres, and most places on Earth don't receive continuous sunlight for months at a time. The ancient Arctic managed to offer all three. Nutrients played a supporting role, quietly making sure the whole system didn't stall. Rivers didn't just bring fresh water, they brought dissolved minerals from rocks and soils far inland. Phosphorus, in particular, is a key element for plant growth. It's part of the molecules that store and transfer energy inside cells, and without it, photosynthesis can't proceed efficiently. As rain fell on distant mountains and plains, it slowly broke down rocks. The resulting particles and dissolved elements were carried into streams, then into larger rivers, and eventually into the Arctic basin. Because the basin was relatively enclosed, these nutrients didn't immediately wash away into the wider ocean. They lingered in the surface layer, available to whatever organisms could make use of them. Azolla, with its built-in nitrogen supply, was especially well positioned to take advantage of this. Other plants and algae might struggle when nitrogen is scarce, even if phosphorus is plentiful. Azolla didn't have that problem. It could grow as long as the other pieces were in place. This created a situation where growth wasn't limited by a single factor. Light was abundant. Nitrogen was internally supplied. Phosphorus and trace elements were delivered by rivers. Temperature was warm enough to keep cellular processes running smoothly. The surface was stable enough to keep the plants in the light. When all of these conditions align, growth can take on a different character. Instead of being slow and constrained, it becomes expansive. Imagine a small patch of Azolla floating near the mouth of a river. The water there is especially fresh and nutrient-rich. The sun hangs in the sky for most of the day. The plants absorb light, build new leaves, and spread outward. As the patch grows, its edges drift into slightly saltier water, but still within the tolerable range. The centre continues to thrive, and the patch expands again. Over time, multiple patches like this could form along the edges of the basin. Gentle currents would move them around, bringing them into contact with one another. Where they met, they merged. Thin green lines became broader mats. Gaps filled in. As the mats grew larger, they began to influence the environment more strongly. By shading the water, they reduced the temperature of the surface layer slightly. Cooler water holds more dissolved gas, including carbon dioxide. This could make it easier for the plants to draw carbon from the water and air. The mats also slowed the movement of water at the surface. This reduced mixing even further, reinforcing the stability of the freshwater layer. Once again, growth fed back into the conditions that supported it. On the microscopic level, the water beneath these mats became a different world from the open surface. Less light reached the depths. Certain types of algae that depended on direct sunlight might have declined. Other organisms that could tolerate lower light or feed on organic material might have increased. This shift in the tiny community of life beneath the mats could influence how organic matter was processed. Some of it would be consumed and recycled near the surface. Some of it would escape that recycling and sink. Every time a leaf of Azolla broke off and drifted downward, it carried with it the carbon that had once been part of the atmosphere. That carbon didn't vanish. It moved from air to plant, from plant to water, from water to sediment. The efficiency of this transfer depended in part on how thick and persistent the mats were. Larger, more continuous coverage meant more plant matter being produced. It also meant a greater chance that some of that material would sink in large enough amounts to overwhelm the local decomposers and reach the seafloor before being fully broken down. The term green explosion might suggest something sudden and violent, but in this context it's more about scale than speed. The expansion of Azolla across the Arctic surface was likely noticeable only when viewed across long spans of time. Year by year it would have been subtle, century by century more apparent. Over thousands of years it became a defining feature of the region. What makes this particularly interesting is how it ties into the broader climate system. As more carbon was drawn into plant matter and buried, the concentration of carbon dioxide in the atmosphere slowly declined. This reduced the greenhouse effect, allowing more heat to escape into space. The cooling wouldn't have been uniform or immediate. Some regions would have felt it more than others. The poles, being more sensitive to changes in heat balance, likely responded first. Seasonal snow might have lingered longer. Ice might have begun to form more readily in winter. These early changes could then feed back into the system. Ice and snow reflect more sunlight than dark water or land. As they expanded, they would bounce more of the sun's energy back into space, reinforcing the cooling trend. This is where the story begins to move from local to global. What started as a set of favourable conditions in a quiet enclosed sea began to ripple outward, influencing patterns of temperature and climate across the planet. But it's important to remember that this wasn't a simple, one-way process. The environment could push back. If cooling became too strong, the growing season in the Arctic could shorten. Less sunlight and lower temperatures could slow Azolla's growth. Fresher water might become more mixed with saltier layers as ice formation and a melting changed circulation patterns. Nutrient delivery could shift as rainfall and river flow changed. In other words, the system had checks and balances. The green mats couldn't expand indefinitely without affecting the very conditions that allowed them to exist. This dynamic tension is part of what makes Earth's climate system so complex. Processes that drive change often carry the seeds of their own limits. Growth alters the environment. The altered environment then reshapes growth. From the perspective of the fern, none of this is intentional. There's no goal, no awareness. It's simply responding to the conditions it finds. But from the perspective of the planet, these responses add up to something that looks very much like regulation. The Arctic, in this period, became a kind of testing ground for this interplay. Its unusual combination of geography and climate made it sensitive to small shifts. The presence of widespread floating vegetation was one of those shifts. As scientists look back at this time, they try to quantify how extensive the Azolla coverage might have been. Was it patchy, covering only certain regions, or did it form nearly continuous mats across much of the basin? Different lines of evidence suggest that at its peak, Azolla could have covered vast areas, potentially most of the Arctic Ocean's surface during the summer months. That kind of coverage would have made it one of the largest plant communities on Earth at the time, not in terms of individual size, but in total area. To get a sense of the scale, imagine a region the size of a modern ocean basin, not dotted with islands or broken by coastlines, but covered in a thin living layer of green. Not a forest you could walk through, not a field you could stand in, but a floating world that moved gently with the water beneath it. Every square metre of that surface would be capturing carbon, fixing nitrogen, and participating in the slow exchange between air, water, and sediment. There's also a human element to how we understand this. Our own experience of time is so short that it's hard to grasp what slow really means in a geological sense. 1,000 years feels like an enormous span in human history. In Earth's history, it's barely a moment. The green expansion of Azolla didn't need urgency. It didn't need speed. It needed consistency. The sun rose and didn't quite set. Rivers flowed and didn't quite stop. The fern grew and didn't quite disappear. Over and over again, the same pattern played out, each cycle adding a little more plant matter, a little more buried carbon, a little more influence on the atmosphere. As you let this scene settle in your mind, try to imagine the quietness of it. No sudden transformations, No dramatic shifts, just a slow, steady layering of cause and effect. The idea that such gentle conditions could lead to a planetary change can feel almost counterintuitive. We're used to thinking of big outcomes coming from big actions. But in Earth's story, some of the most lasting changes have come from processes that are almost easy to miss if you're not looking for them. This alignment of sunlight, fresh water and time created a window in which Azolla could become more than just another floating plant. It became a participant in the planet's long-term climate story. Some changes on Earth arrive with a sound you can almost imagine hearing. A volcano roars, a glacier cracks, a meteor tears through the sky. But the change that followed the spread of Azolla didn't announce itself in any of those ways. It came quietly, carried on the smallest of breaths, hidden in a gas that drifts through the air unnoticed most of the time. It was the slow, invisible movement of carbon, leaving the sky one molecule at a time. To understand what was happening, it helps to picture the atmosphere not as an empty space above the planet, but as a vast, restless ocean of gas. In that ocean, carbon dioxide is one of the many currents. It moves constantly between air, water, land, and living things, part of a cycle that has been running for as long as life has existed. In the warm world of the ancient Arctic, this cycle was already in motion long before Azolla arrived. Carbon dioxide drifted down from the air into the surface of the ocean, dissolving into the water. Plants and microscopic algae used it to build their bodies. When those organisms died, much of that carbon was released back into the environment through decay. Some of it ended up buried in sediments. Some of it made its way back into the atmosphere through volcanic activity and chemical reactions in rocks. For millions of years, these flows had kept the system in a kind of rough balance. Carbon went in, carbon came out, the planet stayed warm. What Azolla did was not to invent a new pathway, but to tilt an existing one. It made the path from air to plant to sediment a little wider and a little more efficient. Every green leaf floating on the Arctic surface was a tiny chemical factory. Sunlight provided the energy. Water supplied hydrogen and oxygen. Carbon dioxide, whether from the air directly or dissolved in the surface water, supplied the carbon. Inside the plant's cells, these ingredients were combined into sugars, starches, and the complex molecules that made up the fern structure. This process, photosynthesis, is so common that it's easy to forget how powerful it is. It takes something invisible and turns it into something solid. It pulls carbon out of the sky and weaves it into leaves you can touch. In most ecosystems, that carbon doesn't stay locked away for very long. A leaf falls, a microbe eats it. The carbon is released as carbon dioxide again. The cycle closes. The difference in the ancient Arctic was not at the point of uptake. Azolla wasn't especially unique in how it captured carbon. The difference was at the point of return. When Azolla died, it didn't always stay where it was. The structure of the Arctic Ocean, with its light surface layer and heavier depths below, created a one-way trip for a portion of that plant material. Once it sank past the boundary between those layers, it entered a zone where the usual recyclers of carbon had a harder time doing their work. Deeper waters held less oxygen. Many of the microbes and small animals that break down organic matter need oxygen to do it efficiently. Without it, their activity slows. The breakdown process becomes incomplete. As a result, a fraction of the carbon that had been pulled from the atmosphere ended up preserved in the form of partially decomposed plant material. This material settled on the seafloor mixed with mud and minerals and was gradually buried by more layers of sediment. From the perspective of the atmosphere, that carbon was gone. Not destroyed, not erased, but removed from the active cycle that connects air, water, and living things. It had been transferred into a long-term storage system deep beneath the ocean. This is what scientists mean when they talk about a drawdown of carbon. It's not a sudden vacuum pulling gas out of the sky. It's a gradual shift in where carbon spends its time. More of it ends up in rocks and sediments. Less of it remains in the air. The process was invisible in every sense. You couldn't see carbon dioxide leaving the atmosphere. You couldn't watch it being built into plant tissue at the level of individual molecules. You couldn't observe it settling into the seafloor once it sank. All you would have noticed, if anything at all, would have been the slow spread of green across the water and the almost imperceptible cooling of the world over many generations. One way to imagine this is to think of the atmosphere as a bank account. Carbon dioxide is the currency. There are deposits and withdrawals happening all the time. Volcanic eruptions, for example, make deposits, adding carbon to the air. Chemical weathering of rocks makes withdrawals, slowly removing carbon from the air and locking it into minerals. Azolla's role was to increase the size of one particular withdrawal pathway. It didn't create a new account, it just made one of the existing transactions a little larger and more consistent. Each summer, as the fern grew under the long polar sun, it pulled in more carbon. Each season, as parts of it died and sank, it transferred some of that carbon into the deep ocean savings account. The key was persistence. For a single season, or even a few centuries, the effect would have been small compared to the total amount of carbon in the atmosphere. But over hundreds of thousands of years, the withdrawals added up. Climate records suggest that during the period associated with widespread Azolla growth, atmospheric carbon dioxide levels dropped significantly. Not to the low levels seen in the ice ages of the recent past, but enough to mark a clear shift away from the greenhouse conditions that had dominated earlier. This drop in carbon dioxide meant less heat was trapped near the planet's surface. The Earth began to radiate more energy back into space. The global temperature curve started to bend downward. Again, this wasn't a dramatic plunge. It was more like a long, gentle slope. The kind of change that's hard to notice unless you're looking at a very long timeline. From the point of view of life on the ground, the effects would have shown up first in subtle ways. Growing seasons might have shortened slightly. Snow might have lingered longer in some regions. The balance between different plant communities could have shifted as cooler conditions favoured some species over others. In the polar regions, these changes would have been more pronounced. The formation of ice, even seasonal ice, can have a strong influence on local climate. Ice reflects sunlight, reducing the amount of energy absorbed by the surface. As ice became more common, it would have reinforced the cooling trend. This is one of the feedback loops that make climate systems so complex. A small initial change in carbon levels can lead to temperature shifts. Those temperature shifts can lead to changes in ice cover. Changes in ice cover can further alter how much sunlight the planet absorbs, amplifying the original effect. Azolla didn't directly create ice, but by contributing to a reduction in atmospheric carbon dioxide, it nudged the system in a direction where ice became more likely. What's remarkable is that all of this traces back to countless ordinary acts of plant growth and decay. A leaf grows, a leaf sinks, a microbe breaks down part of it, a bit of carbon stays behind in the mud. Repeat this cycle millions of times across a vast area, and you begin to change the chemistry of the air above the entire planet. There's another layer to this story that adds to its quiet complexity. Carbon doesn't move between air, water, and sediment in isolation. It's tied to other elements, especially oxygen. When plants like Azolla perform photosynthesis, they release oxygen as a byproduct. In a system where more carbon is being buried and less of it is being returned to the atmosphere, the balance between oxygen and carbon dioxide can shift. Over geological timescales, these shifts can influence the overall composition of the atmosphere. They can affect how easily fires start, how efficiently animals can breathe, and how certain chemical reactions proceed. During the Azolla period, the changes weren't extreme enough to transform the atmosphere in those ways, but they were part of the broader, slow evolution of Earth's air. The ocean itself felt the drawdown of carbon as well. When carbon dioxide dissolves in water, it forms carbonic acid, which can lower the pH of the water. A reduction in atmospheric carbon dioxide can lead to slightly less acidic conditions in surface waters. These changes in acidity can influence the ability of marine organisms to build shells and skeletons made of calcium carbonate. Over time, this can affect the structure of marine ecosystems and the way carbon is stored in the form of mineral deposits on the seafloor. Once again, the story becomes one of interconnected pathways. The growth of a floating fern influences the chemistry of the air. The chemistry of the air influences the chemistry of the water. The chemistry of the water influences the biology of the sea. The biology of the sea influences the sediments that form at the bottom. Each step is small. Together they form a network that spans the entire planet. Scientists studying this period use a variety of tools to trace these changes. They analyse the ratios of different carbon isotopes in fossil shells and sediments. These ratios can reveal whether carbon in the system came more from the atmosphere or from long-term geological sources. Shifts in these ratios during the Azolla period point to an increased removal of atmospheric carbon. They also look at oxygen isotopes, which can provide clues about temperature and ice volume. Changes in these records align with the timing of the carbon drawdown, suggesting a connection between reduced greenhouse gases and global cooling. In some sediment layers, researchers find high concentrations of organic matter that can only reasonably be explained by massive amounts of plant material being deposited over long periods. Chemical markers unique to freshwater plants and cyanobacteria help link this material to Azolla and its microbial partners. None of these clues alone tells the whole story. It's the combination of them that builds a convincing picture. A story of a surface ecosystem that became an efficient pathway for moving carbon from the atmosphere into long-term storage. From a human perspective, it's tempting to see this as a kind of natural solution to a climate problem. A plant grows, carbon levels drop, the planet cools. But the reality is more nuanced. The Azolla Event happened over timescales that dwarf anything we experience in our own lives. The changes took hundreds of thousands, possibly millions of years. The system had time to adjust, to respond, to find new balances. Modern changes to atmospheric carbon levels are happening much faster. The comparison can be useful for understanding the power of biological processes, but it also highlights how different the current situation is in terms of speed and scale. Still, there's something deeply instructive about watching how Earth's own systems have regulated themselves in the past. It shows that life is not just a passenger on this planet. It's an active participant in shaping the environment. In the case of Azolla, that participation was almost accidental. The fern didn't evolve to cool the planet. It evolved to float, to grow quickly, and to take advantage of a bacterial partner that could provide nitrogen. The climate effects were a side consequence of those traits interacting with a particular set of conditions. This brings us back to the idea of feedback loops. Life changes the environment. The environment changes the conditions for life. Over long periods, this dance can lead to entirely new states for the planet. As carbon levels fell and temperatures dropped, the Arctic environment that had supported widespread Azolla growth would eventually begin to change. Colder conditions could shorten the growing season. Increased ice cover could disrupt the stable surface layer. Changes in circulation could bring saltier water to the top. At some point, the system would shift enough that Azolla could no longer dominate the surface as it once had. The drawdown of carbon would slow. Other processes would take on a larger role in controlling the planet's climate. In this sense, the Azolla Event was a chapter, not the entire book. A period where one pathway in the carbon cycle became especially prominent before giving way to others. If you imagine the planet as a living system with many moving parts, this period is like a moment when one part of the system takes on a leading role, not because it's inherently more important than the others, but because the conditions happen to favour it. Let the idea of this invisible drawdown settle in. A process you couldn't see, couldn't hear, and couldn't feel in any immediate way, yet one that slowly changed the balance of heat and air around the entire planet. Somewhere above a calm, green-tinged Arctic sea, carbon dioxide molecules drifted into leaves. Somewhere below, in dark, low oxygen waters, fragments of those leaves settled into the mud. Between those two places a quiet connection formed, linking the sky to the stone through the life of a tiny floating fern. And as that connection repeated itself, year after year, layer after layer, the planet itself began to respond, almost as if it were listening to a whisper that took a very long time to be heard. There wasn't a single morning when the Arctic woke up and found itself cold. No sudden frost swept across the water. No sharp line appeared between a warm world and a frozen one. Instead, the change came in a way that would have been almost impossible to notice in the moment. It arrived in small steps, spread across countless seasons, carried on what you might think of as the planet's own slow breathing. To understand how that cooling began, it helps to think about what carbon dioxide actually does in the atmosphere. Sunlight reaches Earth mostly in the form of visible light. The surface absorbs that energy, and then releases it back upward as infrared radiation, a kind of heat. Carbon dioxide and other greenhouse gases are very good at absorbing some of that outgoing heat and re-radiating it in all directions, including back toward the surface. This process keeps the planet warmer than it would be if the heat escaped freely into space. In the warm world of the ancient Arctic, there was plenty of carbon dioxide in the air. The greenhouse effect was strong. Heat lingered. The balance between energy coming in from the sun and energy leaving the planet leaned toward warmth. As Azolla and other processes slowly drew carbon out of the atmosphere and locked it into sediments, that balance began to shift. With fewer greenhouse molecules in the air, a little more heat escaped into space. The change was subtle at first, more like turning down a thermostat by a fraction of a degree than flipping a switch. But even small changes in that balance can matter, especially in regions that already sit close to a threshold. The Arctic is one of those places. High latitudes receive sunlight at a lower angle, spreading the same amount of energy over a larger area. This means they are naturally cooler than the tropics. They also respond more strongly to changes in the amount of heat the planet retains. A small decrease in greenhouse gases can lead to a relatively larger drop in temperature near the poles. So as carbon dioxide levels declined, the Arctic began to feel the effects first. It wouldn't have been dramatic. Summers were still warm enough to support forests and floating plants. Winters were still milder than anything we would recognise today. But the overall trend was downward. Average temperatures dipped a little. Seasonal contrast became slightly sharper. Think of it like a long, gentle exhale. Each year a tiny bit more heat left the system than before. Each year the baseline shifted just a little. One of the earliest signs of this cooling would have appeared in the way ice behaved. Even in a warm world, there can be moments when temperatures dip low enough for ice to form, especially at night or during the darkest part of the polar winter. In the greenhouse Arctic, that ice would have been rare and short-lived, melting quickly when the sun returned. As the climate cooled, those moments of ice formation would have become more common. Thin sheets of ice might have lasted a little longer into the spring. Patches of snow on land might have taken more time to disappear. Ice is more than just frozen water. It's a powerful player in the climate system because of how it interacts with sunlight. Dark surfaces like ocean water and forests absorb a lot of the sun's energy. Bright surfaces like ice and snow reflect much of it back into space. This creates what scientists call an ice albedo feedback. As more ice appears, more sunlight is reflected. With less energy absorbed, temperatures drop further. That drop allows even more ice to form. It's a reinforcing loop. In the early stages of Arctic cooling, this loop would have been weak, but it was there, waiting to grow stronger. The surface of the Arctic Ocean, which had once been a mostly open, green-tinged expanse during summer, would have begun to show more seasonal variation. Floating mats of Azolla might have faced shorter periods of ideal growing conditions. The long days of continuous sunlight would still arrive, but the window for warm, stable surface water could have narrowed. On land, the forests near the polar circle would have felt the change as well. Trees that thrive in warmer conditions might have found it harder to compete as cooler temperatures, and longer-lasting snow-favoured species better adapted to chillier climates. Over long spans of time, the composition of these forests would have shifted. Rivers feeding into the Arctic basin would have carried different patterns of runoff. Colder climates can alter how water moves across the land. Snowmelt might have become a more prominent part of river flow. Seasonal pulses of fresh water could have changed in timing and intensity. All of these factors fed back into the surface layer of the Arctic Ocean. Changes in freshwater input could influence how stable that layer remained. More mixing between surface and deeper waters could bring saltier water upward, making conditions less favourable for freshwater plants like Azolla. In this way, the cooling that Azolla helped initiate could, over time, make the Arctic less welcoming to the very process that contributed to the cooling in the first place. But in the early phases, the system was still in transition. The drawdown of carbon was ongoing, the temperature trend was still downward. The Arctic was beginning to move away from its long-standing warm state. To appreciate how gradual this was, it's helpful to think in terms of generations rather than years. A single tree growing near the ancient Arctic shore might have lived its entire life without noticing any meaningful difference in climate. But over many generations of trees, the baseline would have shifted enough to change which species could take root and thrive. The same would have been true for the organisms in the sea. Plankton communities might have adjusted slowly. Fish populations could have migrated or adapted to changing conditions. The entire ecosystem would have been in a state of slow, continuous response. From a geological perspective, this kind of gradual change is often recorded in the chemistry of sediments and fossils. Layers of mud and shells on the seafloor can preserve information about water temperature, ice volume, and the composition of the atmosphere at the time they were deposited. Scientists use ratios of different forms of oxygen, known as isotopes, in fossil shells to estimate past temperatures. They use carbon isotopes to track how carbon moved through the system. In records from around the time of the Azolla Event, these chemical signals show trends consistent with a cooling climate and a shift in the global carbon cycle. One of the fascinating aspects of this period is how the Arctic's response may have influenced the rest of the planet. The poles play a key role in driving ocean circulation. Cold, dense water tends to sink and flow toward the equator, while warmer water rises and moves poleward. This circulation helps distribute heat around the globe. As the Arctic cooled, it could have begun to produce denser, colder water more readily. This would have strengthened certain deep ocean currents, potentially altering how heat was transported from the tropics to higher latitudes. Changes in ocean circulation can have far-reaching effects. They can influence weather patterns, rainfall distribution, and the productivity of marine ecosystems in distant regions. In this way, the cooling that began in a quiet polar basin could ripple outward, shaping climates far beyond the Arctic itself. The idea of the planet breathing is a useful one here, even if it's only a metaphor. On long time scales, Earth does take in and release gases in a rhythm of sorts. Volcanic eruptions exhale carbon dioxide into the air. Chemical weathering and biological activity inhale it, pulling it back into rocks and sediments. During the Azolla period, the inhalation side of that rhythm became stronger. The balance tipped toward removal. The atmosphere slowly lost some of its insulating layer. The planet cooled. What makes this especially interesting is that the process didn't require anything extraordinary in the way of physics or chemistry. It relied on the same fundamental reactions that still operate today: plants capturing carbon, organic matter sinking, sediments burying it. The difference was in the scale and efficiency. The unique conditions of the Arctic allowed these ordinary processes to operate over an unusually large area and for an unusually long time without being disrupted. There's also a sense in which the cooling was not just about temperature, but about the distribution of energy across the planet. As greenhouse gas levels dropped, the contrast between equatorial and polar regions likely increased. The tropics would have remained relatively warm, while the poles cooled more noticeably. This growing contrast can strengthen atmospheric circulation. Stronger temperature differences between low and high latitudes can lead to more energetic wind patterns, which in turn can influence ocean currents and weather systems. These changes could have fed back into the Arctic environment itself. Stronger winds might have increased mixing in the surface waters. Changes in precipitation patterns could have altered freshwater input from rivers. Once again, the system reveals itself as deeply interconnected. A change in the atmosphere influences the ocean. A change in the ocean influences the atmosphere. The land, the ice, and the living world all respond in their own ways. As the Arctic began to cool, the floating mats of Azolla would have faced new challenges. Cooler water slows down metabolic processes. Shorter growing seasons limit how much a plant can expand each year. Increased mixing could expose the plants to saltier water or push them into deeper, darker layers. Some years, blooms might have been less extensive. Some regions might have seen Azolla retreat. Other areas, perhaps closer to river mouths or sheltered bays, might have remained strongholds for longer. This patchwork of growth and decline would have influenced how much carbon continued to be drawn down and buried. The system would have been in a kind of negotiation with itself, adjusting to the changes it had helped set in motion. From the standpoint of deep time, this period marks a transition. The Earth was moving away from a long-lasting greenhouse phase and edging toward a cooler state that would, millions of years later, culminate in the ice ages of the more recent geological past. The Azolla Event wasn't the sole cause of that long-term shift, but it appears to have been one of the contributing factors, especially in the early stages. There's something quietly profound about that. A small plant, thriving in a particular set of conditions, becomes part of a chain of events that influences the trajectory of an entire planet's climate for millions of years. If you imagine standing on the shore of that ancient Arctic during this transition, the changes would have been almost impossible to perceive. The water would still stretch out under a bright summer sky. The air would still feel mild. The forest would still grow. But beneath that familiar surface, the balance of energy and carbon was shifting. The system was leaning just a little toward a different future. As centuries passed into millennia, those tiny shifts accumulated. What began as a gentle cooling trend eventually reshaped ecosystems, altered ocean circulation, and set the stage for the colder world that would come much later. This is one of the reasons scientists are so interested in periods like the Azolla Event. They offer a window into how sensitive the Earth's climate system can be to relatively small changes in the carbon cycle. They show how feedback loops can amplify those changes over time. At the same time, they remind us of the difference between geological and human timescales. The cooling that followed Azolla's spread took place over hundreds of thousands of years. It allowed ecosystems time to adapt and migrate. It unfolded at a pace that the planet's systems could absorb. The present-day changes to atmospheric carbon levels are happening much faster, raising different kinds of challenges for life and climate. Still, the ancient story has value beyond comparison. It illustrates a fundamental truth about Earth. The planet is not a static backdrop for life. Life is woven into the planet's physical and chemical processes. Plants, microbes, oceans, and rocks all participate in shaping the climate. In the Arctic of the Eocene, that participation took the form of a slow, invisible drawdown of heat, breath by breath, molecule by molecule. Beneath the calm surface of the ancient Arctic, far below the drifting mats of green and the soft reflections of a sky that barely darkened in summer, there was another world entirely. It was a place of quiet, of slow movement, of particles falling through dim water like a gentle, endless snowfall. This was where the story of Azolla's influence became permanent, where the carbon drawn from the sky took on a different kind of life, one measured not in seasons or years, but in layers of stone and time. When a leaf of Azolla reached the end of its brief existence, it didn't vanish. It changed form. The air-filled spaces that had helped it float collapsed. The structure that once held it at the surface softened and broke apart. Slowly, almost reluctantly, it began to sink. At first, the journey downward was unremarkable. The plant matter drifted through the upper layer of water, passing by tiny animals and microorganisms that fed on organic debris. Some of the carbon locked inside the leaf was released here, breathed out by microbes as they broke down sugars and other compounds. That carbon rejoined the water as dissolved carbon dioxide, and from there, some of it could eventually make its way back into the atmosphere, but not all of it. The Arctic Ocean of that era had a feature that made this descent different from what happens in many parts of the modern sea. Beneath the fresher, lighter surface layer was denser, saltier water that didn't mix easily with what was above. This created a boundary, a kind of invisible threshold. Once sinking material passed through it, the environment changed. Light faded quickly, oxygen levels dropped. The community of organisms capable of feeding on the falling plant matter became smaller and less active. Decomposition slowed. This doesn't mean nothing happened in the deeper water. Microbes were still there, working at their own pace, breaking down what they could. But the process was incomplete. Some of the complex organic molecules resisted being fully dismantled. They settled out of the water column and joined the soft, muddy surface of the seafloor. Over time, this created a blanket of organic-rich sediment. Not a thick layer all at once, but a slow accumulation. A few millimeters here, a thin sheet there. Year after year, century after century, the blanket grew. The seafloor itself was not a smooth, uniform surface. It was shaped by the contours of the basin, by ridges and depressions, by shallow shelves near the edges and deeper plains toward the centre. These features influenced where sinking material tended to collect. In shallower regions, close to the continental margins, sediments from land joined the rain of plant material from above. Rivers delivered fine particles of clay and silt, which spread out over the seafloor when they reached the ocean. These mineral grains mixed with the organic matter, helping to bury it more quickly. In deeper regions, far from the coast, the accumulation was slower. Fewer mineral particles arrived from land. The organic material settled gently, forming dark, fine-grained layers rich in carbon. In both cases, burial was the key. Once organic matter was covered by enough sediment, it became isolated from the water above. Oxygen could no longer reach it easily. Microbial activity slowed to a crawl. The carbon inside those buried plant fragments was effectively removed from the short-term carbon cycle. This is what scientists mean when they talk about long-term carbon storage. It's not that carbon is locked away in a sealed vault. It's that it becomes part of a system where the timescale of its return to the atmosphere stretches from years and centuries to millions of years. Some of that buried carbon would eventually be transformed by heat and pressure deep within the Earth. Over geological time, it could become part of sedimentary rocks, or even be turned into fossil fuels. Some of it might one day be released again through volcanic activity or the slow uplift and erosion of rock. But on the timescale of climate and ecosystems, it was gone. What makes this process especially important in the Azolla story is not just that carbon was buried, but how much and how consistently. The widespread coverage of floating ferns meant that large areas of the Arctic surface were producing organic material at a steady rate. This created a reliable supply of sinking plant matter to feed the sedimentary system below. In many parts of the ocean, productivity is patchy. There are blooms of algae and plankton followed by quieter periods. The supply of organic matter to the seafloor rises and falls. In the ancient Arctic, the long-growing seasons and stable surface conditions may have allowed for more sustained production. This doesn't mean the seafloor was buried under a continuous thick carpet of plant debris. The process was still gradual, but over long spans of time, even a modest increase in the rate of burial can make a significant difference. There's another factor that made the Arctic seafloor an especially effective place for preserving carbon. The deeper waters were not only low in oxygen, they were also relatively isolated from the rest of the global ocean. In many modern ocean basins, deep water is constantly being formed and circulated. cold, dense water sinks in certain regions and then flows along the seafloor, spreading around the globe. This movement brings oxygen into deep waters, which supports the organisms that break down organic matter. The ancient Arctic, being more enclosed, likely had weaker deep water circulation. This meant that oxygen-poor conditions near the bottom could persist for long periods. In such an environment, organic-rich sediments are more likely to be preserved. This kind of setting is sometimes referred to as anoxic or disoxic, meaning that oxygen levels are very low. In these conditions, certain chemical reactions can take place that further stabilize organic carbon, binding it into compounds that are harder for microbes to break down. So the seafloor wasn't just a passive collector of falling leaves, it was an active participant in the process of carbon storage, shaping how much of that material would remain intact and how much would be recycled. From a distance, this might sound like a purely chemical or geological story, but there's a biological side to it as well. The organisms that lived in and on the seafloor sediments played a role in determining what stayed and what went. In oxygen-rich environments, burrowing animals and active microbes can churn sediments, bringing buried material back to the surface where it can be broken down. In low-oxygen environments, this kind of activity is limited. The sediment remains more layered, more orderly, and more effective at sealing away what it contains. The Arctic basin of that time likely had fewer large burrowing organisms than many modern seas. This would have further enhanced the preservation of organic matter. As layers of sediment built up, they created a physical record of what was happening above. Each layer captured a snapshot of the material that was falling through the water at that time. Changes in the amount and type of organic matter in these layers reflect changes in the surface ecosystem. When scientists drill into the seafloor and extract long cores of sediment, they are essentially reading this history in reverse. The deepest layers represent the oldest periods, the upper layers represent more recent ones. In cores taken from the Arctic, researchers have found thick sections of dark, organic-rich sediment dating to the time associated with widespread Azolla growth. Chemical analyses of these layers reveal high concentrations of compounds that are characteristic of freshwater plants and cyanobacteria. These compounds, often referred to as biomarkers, act like molecular fingerprints. They don't tell you exactly what the surface looked like, but they provide strong clues about what kinds of organisms were contributing to the sediment. In some cores, these Azolla-rich layers are meters thick. That might not sound like much, but when you consider that each centimetre of sediment can represent hundreds or thousands of years, it becomes clear just how long this process was active. There's a certain elegance to this method of discovery. No one can travel back to the Eocene Arctic and watch the plants sink. But by looking at the chemical traces left behind, scientists can reconstruct the outlines of a story that played out over immense spans of time. The sediments also preserve information about the conditions in the water at the time they were deposited. The types of minerals present, the size of the particles, and the ratios of certain elements can all point to things like water temperature, salinity, and oxygen levels. In the Azolla layers, these signals often align with what we would expect from a stratified low-oxygen environment. This supports the idea that the Arctic basin was well suited to preserving organic carbon during this period. It's also worth noting that not all of the carbon burial happened in a perfectly smooth, continuous way. The environment would have changed over time. Periods of stronger mixing, perhaps driven by storms or shifts in circulation, could have brought oxygen-rich water into deeper layers, increasing decomposition for a while. River input might have varied with climate, altering the supply of fresh water and nutrients. Volcanic activity elsewhere on the planet could have influenced atmospheric composition and temperature, indirectly affecting conditions in the Arctic. These fluctuations would have left their mark in the sediment record as variations in the thickness and composition of the layers. Some sections might show especially high organic content. Others might show more mineral-rich deposits. From a storytelling perspective, it's tempting to imagine a steady rain of green leaves sinking into a perfectly still sea, but the reality was likely more complex. The system breathed in its own way, with periods of greater and lesser activity. Still, the overall trend appears clear. For a significant span of time, the Arctic basin functioned as an efficient sink for organic carbon. The widespread growth of Azolla at the surface provided the raw material. The stratified, low-oxygen depths provided the conditions for preservation. Together, they created a pathway that moved carbon from the atmosphere into the Earth's crust. There's something quietly dramatic about that, even if the process itself was gentle. The sky, the water, and the stone were linked by the life of a tiny plant. Each leaf that sank became part of a geological archive, a physical trace of a moment when the planet's climate system leaned in a particular direction. As the sediments accumulated, they also influenced the physical structure of the seafloor. Thick layers of soft, organic-rich mud can behave differently under pressure than more mineral-heavy sediments. Over time, as these layers were buried deeper, they compacted and changed. In some cases, this kind of sediment can become a source of hydrocarbons if subjected to enough heat and pressure. While the Azolla Event itself didn't directly create oil or gas fields in the way we think of them today, it contributed organic material to the kind of sedimentary environments that, much later, can play a role in those processes. This adds another layer of connection between ancient climate events and the resources that humans use in the present. The carbon that Azolla pulled from the atmosphere didn't just cool the planet. Some of it became part of the geological foundation that would, millions of years later, be tapped as a source of energy. That connection can feel strange to consider. A floating fern in a warm, ancient Arctic helping to shape the conditions that would eventually lead to both a cooler world and the formation of substances that modern societies rely on. It highlights how long and winding the paths of cause and effect can be in Earth's history. From the perspective of the planet's carbon cycle, the burial of organic matter in sediments is one of the main ways carbon leaves the fast surface-level system and enters the slow, deep one. The fast system includes the atmosphere, the oceans, and living organisms. Carbon moves through this system on timescales of years to centuries. The slow system includes rocks, sediments, and the Earth's interior. Carbon moves through this system on timescales of millions of years. The Azolla Event can be seen as a moment when the connection between these two systems became especially active. The flow of carbon from the fast system into the slow one increased. This shift didn't just affect temperature, it also influenced the long-term evolution of the atmosphere and oceans. Over geological time, changes in carbon storage can affect things like ocean acidity, nutrient availability, and the balance of gases in the air. These changes, in turn, can shape the evolution of life. Certain groups of organisms thrive under specific chemical conditions. Others struggle. The long-term cooling trend that followed the Azolla period would eventually favour species adapted to cooler, more seasonal climates. In this way, the sinking of plant matter into Arctic sediments was part of a chain of events that reached far beyond the seafloor. It touched ecosystems on land, patterns of ocean circulation, and the overall trajectory of the planet's climate. If you imagine standing on the surface of that ancient sea, it would be hard to connect what you saw with what was happening far below. The green mats drifted, the water shimmered, birds flew overhead. Everything at the surface seemed alive and immediate. But beneath that scene, the slow work of burial was underway. Each particle of organic matter that reached the bottom became part of a growing archive, a quiet testimony to the exchange between life and the planet's chemistry. This contrast between the lively surface and the silent depths is one of the most striking aspects of the story. The same plant that floated in the sun became, in death, a contributor to a dark, low-oxygen world where time moved at a different pace. It's also a reminder that not all of Earth's most important processes happen where we can easily see them. Some of the most influential changes unfold in places that are hidden from view, in layers of mud, in deep water, in the slow compression of sediment into stone. As scientists continue to study these sediment cores, they refine their understanding of how efficient the Azolla system really was. They estimate how much carbon could have been buried, how quickly the layers accumulated, and how these numbers compare to changes in atmospheric carbon dioxide recorded elsewhere. These estimates are not exact. They come with uncertainties. But they consistently point to a period of enhanced carbon burial that aligns with the timing of Arctic Azolla blooms and the onset of global cooling trends. This convergence of evidence strengthens the idea that the seafloor played a crucial role in turning a biological event at the surface into a climatic event for the planet. The shift from a warm, green Arctic to a colder, more restrained world didn't happen like the closing of a door. It was more like the slow turning of a season that never quite decided when to end. For a long time, the signs were subtle, scattered across landscapes and oceans in ways that only became obvious when you stepped back and looked across vast stretches of time. At the surface of the Arctic Ocean, the familiar patterns of floating plants and open water began to feel different. Summers were still bright, and the sun still traced its long, looping path around the sky, but the warmth it brought no longer lingered in quite the same way. The surface water cooled a little more quickly when clouds passed. The growing season for floating ferns and other organisms shortened by small, almost unnoticeable amounts. These changes didn't erase the green mats overnight. Azolla and its companions were resilient. They could still take advantage of long days and fresh surface water. But the balance they depended on was beginning to tilt. As average temperatures dropped, the behaviour of water itself began to change. Colder water is denser than warmer water, and as the surface cooled, it became heavier. This made it more likely to sink and mix with the saltier water below. The stable layering that had once protected the floating plants from deeper, harsher conditions began to weaken. When mixing increased, saltier water could rise closer to the surface. For freshwater plants, this was a challenge. Even small increases in salinity can affect how plant cells manage the flow of water and nutrients. Growth slows, stress increases. Some patches of floating vegetation might have struggled more than others, especially those farther from the steady supply of fresh water near river mouths. This created a patchwork across the Arctic surface. In some areas, green mats persisted, supported by local conditions that still favoured them. In other regions, open water became more common. The once more continuous green fields began to break into scattered islands. On land, the changes were also unfolding, though just as quietly. Forests near the polar regions began to show signs of shifting composition. Trees that favoured warmer, more stable climates found themselves competing with species better adapted to cooler temperatures and more pronounced seasonal cycles. Snow that once melted quickly in spring might have lingered a little longer on the ground. This could delay the start of the growing season for plants on land, affecting the entire food web. Insects that depended on early blooms might have appeared later. Birds that timed their migrations to match the availability of food would have adjusted their schedules. These small shifts, repeated over many generations, gradually reshaped the ecosystems of the high latitudes. One of the most important changes was happening at the boundary between the ocean and the atmosphere. As ice began to appear more regularly during the colder months, the way the Arctic exchanged heat with the sky changed. Open water releases heat into the air. Ice acts like a lid. When a thin layer of ice forms on the surface of the ocean, it slows the transfer of heat from the water below to the cold air above. This can make the air colder while keeping the water beneath slightly warmer. At the same time, ice reflects sunlight. Instead of absorbing the sun's energy and warming up, an icy surface sends much of that energy back into space. This reduces the overall amount of heat entering the system. Together, these effects reinforce cooling. More ice leads to less heat absorption, which leads to lower temperatures, which leads to more ice. In the early stages of this transition, ice may have appeared only seasonally, thin sheets forming during the darkest part of winter, then melting away when the sun returned. But even this seasonal presence was enough to begin altering the energy balance of the region. The Arctic was becoming a place where cold could gain a foothold. As the polar regions cooled, the effects were not confined to the top of the world. The Earth's climate system is connected by moving air and water. Changes in one region can influence conditions in others. Ocean currents play a major role in this connection. They act like conveyor belts, carrying warm water from the tropics toward the poles and cold water back toward the equator. This movement helps distribute heat around the planet. As the Arctic cooled and began producing colder, denser water more consistently, it likely influenced the strength and pattern of these deep ocean currents. Denser water tends to sink and spread along the sea floor, forming part of the global circulation system known as the thermohaline circulation. Changes in this circulation can affect how much heat is delivered to different regions of the world. If less warm water reaches higher latitudes, those regions can cool further. If the return flow of cold water to lower latitudes changes, it can influence climates far from the poles. In this way, the cooling that began in the Arctic had the potential to ripple outward, touching distant coastlines and shaping weather patterns in places that would never see a floating fern or a polar night. The atmosphere responded as well. As the temperature contrast between the equator and the poles increased, the large-scale circulation of air became more energetic. Stronger temperature gradients can drive stronger winds. These winds, in turn, influence ocean currents by pushing surface waters and shaping patterns of upwelling and downwelling. They also affect how moisture is transported around the globe, influencing where rain falls and where dry conditions persist. The planet was not just cooling, it was reorganizing how energy and water moved across its surface. From the perspective of life, this reorganization created both challenges and opportunities. Some species found themselves in environments that no longer suited them. Others found new niches opening up. In the oceans, changes in temperature and circulation could alter the distribution of nutrients. Areas that once supported rich plankton communities might have become less productive. Other regions might have seen an increase in nutrient supply as currents shifted. Plankton form the base of most marine food webs. Changes in their abundance and composition can cascade upward, affecting fish, marine mammals and birds. On land, shifting climate zones could push plant communities toward or away from the poles. Grasslands might expand into areas once dominated by forest. Forests might retreat from regions that became too cold or too dry. These changes would not have been synchronized across the globe. Different regions would have responded at different rates, depending on their geography, their proximity to oceans, and the specifics of their local climate. One of the striking things about this period is how it marks the beginning of a long-term trend toward a cooler Earth. The planet has moved in and out of warm and cold phases many times throughout its history, but the transition associated with the Azolla Event appears to be one of the early steps toward the icehouse conditions that would later define much of the recent geological past. An icehouse world is one where large permanent ice sheets exist at the poles. The modern Earth is in such a state with vast ice caps in Antarctica and Greenland. The greenhouse world of the Eocene had none of these. The transition between these states is not a simple flip. It involves a series of intermediate phases where ice appears seasonally, then more persistently, then in larger and larger accumulations. The period following widespread Azolla growth fits into this middle ground. Ice was becoming more common, but it had not yet taken over the landscape. If you could travel forward through time from the height of the Azolla Event, you would see the Arctic gradually lose its green surface and gain a more variable, often icy one. You would see forests retreat southward. You would see the ocean's surface shift from calm and layered to more mixed and dynamic. These changes would have unfolded over millions of years, far beyond the scope of any single species' lifespan. Life adapted as it always does, through a combination of migration, evolution, and extinction. Some organisms would have tracked their preferred conditions by moving toward lower latitudes or different elevations. Others would have adapted to the new climate. Still others would have disappeared, replaced by species better suited to the cooler world. From a human standpoint, it can be tempting to look at this long-term cooling as a single, coherent story. But in reality, it would have been made up of many smaller stories, regional climates shifting in different ways, local ecosystems responding in their own patterns. In some places, the cooling might have brought increased rainfall. In others, it might have led to drier conditions. Mountain ranges could have developed glaciers that fed rivers in new ways. Coastal regions might have experienced changes in sea level as ice locked up water on land. The transformation from green seas to icy shores was not uniform. It was a mosaic of changes playing out across a diverse planet. The role of carbon in this transformation remained central. As long as more carbon was being stored in sediments and rocks than was being released back into the atmosphere, the cooling trend could continue. Over time, other processes would come into play, such as changes in volcanic activity and the weathering of newly uplifted mountain ranges, which also influence atmospheric carbon levels. The Azolla Event was one piece of this larger puzzle. It contributed to a period where the planet's carbon balance shifted towards storage rather than release. As the Arctic environment became less favourable for widespread floating vegetation, the efficiency of that particular carbon pathway would have declined. Other pathways would have taken on more importance. Chemical weathering of rocks on land, for example, is another major way carbon is removed from the atmosphere over long timescales. When rainwater, slightly acidic due to dissolved carbon dioxide, reacts with certain minerals, it can lock carbon into solid compounds that eventually end up in sediments and rocks. As mountain ranges rise through tectonic activity, they expose fresh rock to the elements, increasing the rate of weathering. This can draw down atmospheric carbon and contribute to cooling. These geological processes operate on timescales similar to those of large climate shifts. Over millions of years, they can have effects comparable to those of biological processes like the Azolla blooms. This interplay between biology and geology is one of the defining features of Earth climate history. Living things influence the atmosphere and oceans. The movement of continents and the rise of mountains influence living things. The two are intertwined in a long ongoing conversation. As the Arctic moved toward a cooler state, the character of that conversation changed. The once dominant role of floating ferns gave way to other influences. The surface of the ocean became more exposed to wind and mixing. Ice formation altered the exchange of heat and gases with the atmosphere. The deeper circulation of the ocean adjusted to new temperature and salinity patterns. The seafloor, meanwhile, continued to hold its archive of the green world that had once floated above it. Layers of organic, rich sediment remained buried, preserving a record of a time when the Arctic was a place of calm waters and widespread floating vegetation. In this sense, the transformation from green seas to icy shores was not a complete erasure of the past. It was a layering. Each new state of the planet built upon the remnants of the old. Even today, in the modern Arctic, scientists can drill into the seafloor and recover samples that contain traces of that ancient warm world. Chemical markers in those sediments tell stories of freshwater plants and low oxygen conditions, of carbon burial and climate change. These traces serve as reminders that the landscapes and climates we know are just one chapter in a much longer book. There's something quietly grounding about that idea. The world has been many things. It has been warmer and colder, greener and icier, quieter and more turbulent. Each state has left its mark, not just in the rocks and sediments, but in the pathways of evolution and the distribution of life. The shift we're following here is one of those moments when the planet leaned into a new identity. As the Arctic cooled, it began to resemble, in small ways at first, the place we recognise today. Seasonal ice, more pronounced winters, a surface that alternated between open water and frozen cover. Of course, the modern Arctic is the result of many additional changes that came long after the Azolla period. The formation of the Antarctic ice sheet, the uplift of major mountain ranges, and the rearrangement of continents all played their roles. But the early cooling trend that followed the drawdown of carbon set the stage for those later developments. If you imagine standing at the edge of that ancient sea during this transitional period, you might have noticed a growing unpredictability. Some summers would feel much like the ones before, with wide stretches of green and open water. Other years might bring more ice, more cold, more disruption. The world would have felt as though it was testing out a new rhythm, not yet settled, not yet committed. That sense of experimentation, of the planet trying on different states, is a useful way to think about Earth's climate history. It's not a straight line from one condition to another. It's a series of adjustments, feedbacks, and responses. The story of a floating forest at the top of the world didn't come from a single dramatic moment of discovery. There was no lone scientist standing on the deck of a ship, holding up a dripping sample and realizing all at once that a tiny plant had once helped reshape the planet. Instead, the understanding grew the way the sediments themselves did, slowly, layer by layer, built from small clues gathered over many years and across many disciplines. To begin with, there was a puzzle. For a long time, scientists studying Earth's climate history knew that something significant had happened in the Arctic during the Eocene period. Chemical records from rocks and fossils suggested that the region had once been much warmer and fresher than it is today. There were hints of a major change in the global carbon cycle around the same time, but the details were fuzzy. The Arctic Ocean was remote, difficult to access, and mostly hidden beneath thick ice for much of the year. Its sea floor, where the most direct evidence would be preserved, was largely unexplored. The challenge was simple to describe and hard to solve. How do you study the history of a place you can barely reach? The first steps came not from the Arctic itself, but from other parts of the world. Scientists had been drilling into ocean sediments for decades, pulling up long cores of mud and rock from the seafloor in the Atlantic, Pacific and Indian Oceans. These cores revealed a rich history of Earth climate, preserved in layers of tiny shells, minerals and organic matter. In those records, researchers noticed a pattern. Around the middle of the Eocene, there was a noticeable shift in carbon isotopes, a chemical signal that often points to changes in how carbon is moving through the Earth system. This shift appeared in multiple locations, suggesting it was global rather than local. At the same time, other evidence pointed to a cooling trend that began after a long period of warmth. Something, somewhere, had changed the balance of carbon between the atmosphere, the oceans, and the sediments. The Arctic, with its unique geography and potential for preserving organic material, became a prime suspect. But suspicion isn't evidence. To test the idea, scientists needed to get their hands on the sediments beneath the Arctic Ocean itself. That was easier said than done. For much of the 20th century, the Central Arctic was one of the least accessible regions on Earth. Thick, shifting ice made it difficult for ships to operate. Even reaching the area required careful planning, specialised vessels, and a willingness to work in some of the harshest conditions on the planet. The breakthrough came with international cooperation and advances in technology. Icebreakers, research ships designed to push through frozen seas, opened up new possibilities. Drilling equipment capable of operating in deep water and cold conditions made it possible to extract cores from the seafloor. One of the most significant efforts was a mission known as the Arctic Coring Expedition, or ACEX, carried out in the early 2000s. This project brought together scientists and ships from multiple countries, all working toward the same goal: to drill into the sediments beneath the Central Arctic Ocean and recover a continuous record of its past. The location they chose was the Lomonosov Ridge, an underwater mountain range that stretches across the Arctic basin. This ridge rises high enough above the surrounding seafloor to preserve thick, relatively undisturbed layers of sediment. It was, in geological terms, a good place to read a long history. The logistics were complex. Icebreakers had to clear and maintain a working area in the shifting pack ice. The The drilling ship had to hold its position with precision, even as the ice and currents tried to push it off course. Crews worked in cold, challenging conditions to bring up each section of core. When the first cores came up, they didn't look like much to the untrained eye. Long, cylindrical sections of mud and rock, wrapped in plastic, stacked carefully on the deck. But to the scientists on board, these were pages from a book that hadn't been opened in tens of millions of years. As the cores were split open and examined, something unusual began to appear. Instead of the pale, mineral-rich sediments typical of deep ocean floors, there were dark, organic, rich layers. These layers were thick, sometimes meters deep, and they stood out sharply from the material above and below. Dark sediments often mean one thing: life. The next step was to figure out what kind of life had contributed to these layers. For that, scientists turned to a combination of microscopy, chemistry, and molecular analysis. Under the microscope, they found fragments of plant material. Spores and pollen grains, tiny and often beautifully patterned, told a story of vegetation that had once grown nearby. Some of these pollen types matched plants known to thrive in warm, temperate conditions, not the cold, barren landscapes we associate with the Arctic today. But pollen alone couldn't explain the sheer volume of organic material. There had to be something else, something more widespread. This is where chemistry became especially important. Scientists analysed the cores for specific organic compounds known as biomarkers. These are molecules that are produced by certain groups of organisms and can persist in sediments for millions of years. They act like chemical signatures, pointing to the types of life that were present when the sediment was deposited. In the dark Arctic layers, researchers found high concentrations of compounds associated with freshwater plants and cyanobacteria. One group of molecules in particular stood out. They were characteristic of Azolla and its bacterial partner. This was a turning point. The presence of these biomarkers suggested that large amounts of Azolla-like material had been raining down into the Arctic basin for an extended period. The thickness of the layers implied that this wasn't a brief event. It was sustained over a long span of time. To put this into context, imagine trying to cover the floor of a deep lake with leaves. A single tree shedding its foliage wouldn't make much of a dent. You would need an entire forest shedding year after year to build up a noticeable layer. The sediment cores were telling scientists that the Arctic surface had once been producing organic material at a scale large enough to create what amounted to a submerged forest, preserved in mud. Of course, extraordinary claims require careful testing. Researchers didn't stop at one line of evidence. They compared the Arctic cores with records from other parts of the world. They looked at changes in carbon and oxygen isotopes. They examined fossil assemblages and mineral compositions. One of the key questions was whether the Arctic layers could be explained by material washed in from land, rather than by plants growing at the surface of the ocean. Rivers can carry large amounts of organic debris into the sea, especially during floods. But the chemical fingerprints didn't match that scenario. The biomarkers pointed specifically to freshwater floating plants and cyanobacteria, not to the mix of terrestrial vegetation you would expect from river runoff alone. The structure of the sediments also provided clues. The layers were fine-grained and relatively uniform, suggesting a slow, steady rain of material from above, rather than the chaotic deposits left by sudden floods or landslides. Another piece of the puzzle came from the way the layers were arranged. The Azolla-rich sediments were sandwiched between more typical marine deposits. This indicated a distinct period when conditions in the Arctic were different from both before and after. The timing of this period, based on radiometric dating and fossil correlations, lined up with the middle of the Eocene, the same time when global records showed a shift in the carbon cycle and the beginning of a cooling trend. The pieces were starting to fit together. Still, scientists wanted to go further. They wanted to estimate how much carbon might actually have been buried during this period. This required combining information about the thickness of the organic rich layers, their carbon content, and the area over which they likely extended. By mapping the distribution of similar sediments across the Arctic basin and using models to fill in gaps where cores hadn't been taken, researchers could make rough estimates of the total amount of carbon stored in these deposits. The numbers were large enough to plausibly account for a significant portion of the observed drop in atmospheric carbon dioxide during that time. This didn't mean Azolla was the only factor involved. As with most things in Earth's climate system, multiple processes were at work, but it did mean that the floating fern and its microbial partner had played a role big enough to leave a global signature. What's particularly interesting about this discovery is how interdisciplinary it was. It didn't belong to a single field of science. Geologists provided the drilling technology and the expertise to interpret sediment layers. Chemists analysed the molecular composition of the organic material. Biologists identified the types of plants and microbes that could have produced those molecules. Climate scientists built models to test how changes in carbon storage might affect global temperatures. Each piece of the story depended on the others. Without the cause, there would be no physical record. Without the chemistry, there would be no way to identify the source of the organic material. Without the climate models, there would be no way to connect the Arctic event to global changes. There's also a human story woven into this. The process of drilling in the Arctic required cooperation between nations that don't always work together easily. Ships from different countries shared data, equipment, and expertise. Scientists from around the world contributed to analysing the samples and interpreting the results. In this sense, the discovery of the lost Arctic forest was not just a scientific achievement, but a collaborative one. As more data came in, the picture became clearer, but also more nuanced. Researchers began to see that the Azolla event was not a single, uniform episode. There were likely multiple phases of growth and decline, influenced by changes in climate, ocean circulation, and river input. Some layers showed especially high concentrations of Azolla biomarkers, suggesting periods of particularly extensive blooms. Other layers showed lower concentrations, hinting at times when conditions were less favourable. This pattern fits with the idea of a system in motion rather than a static state. The Arctic environment would have responded to broader changes in the planet's climate, just as the planet's climate responded to what was happening in the Arctic. One of the most powerful aspects of the sediment record is that it preserves not just what happened, but how it changed over time. The gradual thinning of the organic-rich layers toward the top of the sequence suggests a decline in Azolla dominance as the Arctic became colder and more mixed. Above those layers, more typical marine sediments take over, marking a return to conditions less favourable for widespread freshwater plants. This transition is, in a way, a geological echo of the story we've been following. The rise of green seas, the slow drawdown of carbon, the onset of cooling, the retreat of the floating forest. There's something quietly satisfying about seeing that arc written in stone. Modern technology continues to refine this picture. High-resolution imaging allows scientists to examine sediment layers in fine detail. Advances in molecular analysis make it possible to identify even smaller and more specific biomarkers. Computer models grow more sophisticated, capable of simulating complex interactions between ocean circulation, climate, and biological productivity. Each new tool adds another layer of understanding, another line of evidence that can confirm or challenge existing ideas. At the same time, there's a sense of humility in this work. The record is incomplete. Not every part of the Arctic seafloor has been drilled. Not every layer is perfectly preserved. There are uncertainties in dating and interpretation. Science, in this context, is less about finding a single, definitive answer, and more about building a story that fits the evidence as well as possible, while remaining open to revision as new information comes in. The idea of a lost forest beneath the ocean floor is, of course, a metaphor. There were no towering trees waving in the water. But in terms of biomass and carbon storage, the mats of Azolla and the layers of sediment they produced were forest-like in their scale and impact. They represent a moment in Earth's history when a simple, floating plant community covered an area large enough and persisted long enough to leave a lasting imprint on the planet's climate. There's also something compelling about the way this discovery connects the present to the deep past. When scientists examine these sediment cores, they are physically touching material that was once part of a living system millions of years ago. A fragment of plant matter that floated on a warm Arctic sea, shaded by a sun that never quite set, can end up in a laboratory, analysed under a microscope, its chemical signature read like a message across time. That connection can feel almost personal, even though the timescales involved are far beyond anything we experience in our own lives. It also highlights the role of the oceans as Earth's great archive. Land surfaces are constantly being reshaped by erosion, weathering, and tectonic activity. Ocean sediments, especially in deep, stable basins, can preserve records that span tens of millions of years. In the case of the Arctic, the combination of low oxygen conditions and steady sedimentation created a particularly good environment for preserving organic material. Without those conditions, much of the evidence for the Azolla Event might have been lost. The fact that it wasn't lost allows us to tell this story at all. As scientists continue to explore the Arctic and other remote regions, they are likely to uncover more surprises. The deep ocean remains one of the least studied parts of the planet. Each new core, each new sample, has the potential to reveal something unexpected about Earth's past. The discovery of the Azolla layers serves as a reminder of how much there still is to learn. It shows that even in a world we think we understand fairly well, there are chapters of the planet's history waiting quietly beneath our feet, or in this case, beneath miles of water and ice. From a broader perspective, this story also offers a way to think about how we learn about the Earth at all. We can't go back in time. We can't observe ancient climates directly. We have to infer them from traces, from indirect signals, from the marks they left behind in rocks, chemicals, and fossils. That process requires imagination, but it also requires rigour. Hypotheses are tested against data. Models are checked against observations. Ideas are refined or discarded as new evidence comes in. The story of the lost Arctic forest is not just a tale about a floating fern and a cooling planet. It's also a story about human curiosity and persistence, about ships pushing through ice, about scientists spending years analysing tiny molecules, about international teams working together to piece together a puzzle that spans millions of years. In that sense, there's a parallel between the slow accumulation of sediment on the seafloor and the slow accumulation of knowledge in science. Both are built from small pieces, both take time, both can eventually reveal something much larger than any single piece would suggest. When you step back from the details of sediment cores, chemical fingerprints, and ancient maps of drifting continents, the Azolla Event leaves behind a broader impression that feels both simple and surprisingly deep. A tiny plant growing quietly on the surface of a remote ocean became part of a process that influenced the temperature of an entire planet. That idea alone carries a certain weight, not because it points to a single cause and effect, but because it reveals something fundamental about how climate power really works. Climate, in the way Earth experiences it, is not driven by one force acting alone. It emerges from countless interactions between air, water, rock, and life. Some of those interactions are loud and obvious, like volcanic eruptions or shifting continents. Others are almost invisible, unfolding in places we rarely think about, through organisms we barely notice. The Azolla Event belongs firmly in that second category. One of the clearest lessons it offers is that scale does not always come from size. Azolla itself is small. Each individual plant is fragile, easily torn apart by waves or eaten by tiny animals. On its own, it has no more presence than a speck of green floating on water. But when conditions allow it to spread across a vast area, and when that spreading continues for long enough, its collective effect becomes something entirely different. This idea shows up again and again in Earth's history. Coral polyps, each one a small, soft-bodied creature, can build reefs that stretch for hundreds of kilometers. Single-celled plankton can influence the chemistry of the oceans and the composition of the atmosphere. Bacteria in the soil can shape the fertility of entire landscapes. Climate power, in this sense, often belongs not to the biggest or the strongest, but to the most persistent. The Azolla Event demonstrates how a biological process can become part of the planet's long-term regulation system. By drawing carbon dioxide out of the atmosphere and moving it into sediments, the floating fern didn't just change its local environment, it altered the balance of energy between the Earth and space. That balance, sometimes called the planet's energy budget, is at the heart of climate. The Earth receives energy from the sun and loses energy by radiating heat back into space. The difference between those two flows determines the average temperature of the planet. Greenhouse gases like carbon dioxide influence how much of that outgoing heat is trapped. By reducing the amount of carbon dioxide in the air, the Azolla-driven carbon burial allowed more heat to escape. Over long periods, this led to a cooler world. What's important here is not just the outcome, but the pathway. The process didn't require a sudden, external trigger. It didn't depend on a dramatic event like an asteroid impact. It arose from the normal functioning of life in a particular set of conditions. This highlights another key lesson. The climate system is sensitive to changes in the flow of carbon, even when those changes come from processes that, on their own, seem ordinary. Plants photosynthesize, organic matter sinks, sediments accumulate. These things happen all the time. What made the Azolla Event special was the way these processes lined up over a large area and a long duration, creating a sustained shift in the carbon cycle. From a scientific perspective, this reinforces the idea that climate is not just a matter of physics and chemistry, it's also deeply biological. Living organisms are not passive passengers in the climate system, they are active participants. This participation takes many forms. On land, forests influence how much carbon is stored in biomass and soil. They affect how much water evaporates into the atmosphere, which can influence rainfall patterns. They change how much sunlight is reflected or absorbed by the surface. In the oceans, plankton and other organisms influence the flow of carbon and nutrients between surface waters and the deep sea. They affect how much carbon dioxide the ocean can absorb from the air. They shape the structure of marine food webs, which in turn influence how organic matter is processed and buried. The Azolla Event is a particularly striking example because it happened in a place where the effects of biological activity could be preserved and amplified. The Arctic Basin acted like a funnel, channeling carbon from the atmosphere into long-term storage in sediments. Another lesson comes from the timescale involved. The changes associated with the Azolla Event unfolded over hundreds of thousands, possibly millions, of years. This allowed the planet's systems to adjust gradually. Ecosystems had time to respond. Species could migrate, adapt, or evolve. Ocean circulation patterns could shift and settle into new configurations. The atmosphere could reach new balances between greenhouse gases and temperature. This slow pace is very different from the rapid changes that can occur when large amounts of carbon are added to the atmosphere in a short time. In the Azolla case, the carbon flow moved in the opposite direction, from air to rock, and it did so steadily rather than suddenly. The contrast between these two modes of change is one of the reasons the Azolla Event attracts attention in discussions about climate. It offers a natural example of large-scale carbon removal driven by biological processes, but it also shows how slow such processes can be when measured against human timescales. Another important takeaway is the role of feedback loops. The Azolla Event did not operate in isolation. It was part of a network of interactions that reinforced and eventually limited its own influence. As carbon levels fell and temperatures dropped, the Arctic environment began to change. Ice became more common. Surface waters mixed more. Conditions for widespread floating vegetation became less favourable. This, in turn, reduced the efficiency of the carbon burial pathway that Azolla had supported. In other words, the system pushed back. This kind of self-limiting behaviour is common in Earth's climate history. Processes that drive change often create conditions that eventually slow or reverse that change. This doesn't mean the system always returns to its original state. It can settle into a new one, but it does mean that no single influence tends to dominate indefinitely. Understanding this dynamic helps explain why Earth's climate has oscillated between different states over geological time rather than moving steadily in one direction. The Azolla Event also underscores the importance of geography. The same plant in a different place might not have had the same effect. It was the unique combination of the Arctic's enclosed basin, freshwater input, stratified waters, and long summer days that allowed Azolla to become so widespread and to feed so effectively into the sedimentary system. This suggests that climate power is often about context. The impact of a given process depends on where and when it happens, and on how it interacts with the surrounding environment. In modern terms, this can be a useful reminder. Changes in one region of the world can have effects that extend far beyond that region, especially when they influence major pathways in the carbon cycle or energy balance. Another lesson lies in the way scientists came to understand the Azolla Event in the first place. It wasn't obvious. The surface of the modern Arctic doesn't give any hint that it was once a place of widespread floating vegetation. The discovery came from careful analysis of hidden records, preserved deep beneath the seafloor. This speaks to the importance of looking beyond what's immediately visible when trying to understand complex systems. Climate, both past and present, leaves traces that are not always on the surface. They can be written in subtle chemical ratios, in the composition of sediments, in the distribution of fossils. The ability to read those traces requires patience, technology, and a willingness to connect evidence from different fields. There's also a broader philosophical lesson here, one that goes beyond climate science. The Azolla Event reminds us that influence doesn't always come from force. It can come from consistency. A single Azolla plant does almost nothing. 1 trillion of them, growing and sinking year after year, can become part of a process that reshapes a planet's climate. The same principle shows up in many areas of Earth's history. Small tectonic movements, repeated over millions of years, can build mountain ranges. Tiny chemical reactions, repeated endlessly, can change the composition of the atmosphere. This perspective can shift the way we think about cause and effect. Instead of looking for a single dramatic trigger, it encourages us to pay attention to ongoing processes and how they accumulate. Another point worth considering is how the Azolla Event fits into the idea of Earth as a system that can regulate itself, at least to some extent. There is a long-standing concept in Earth science sometimes referred to as the Gaia hypothesis, which suggests that life and the environment form a self-regulating system that tends to maintain conditions suitable for life. The Azolla Event can be seen, cautiously, as an example of this kind of interaction. A warm, carbon-rich atmosphere created conditions that allowed a particular plant to thrive. That plant, in thriving, removed carbon from the atmosphere, contributing to cooling. The cooling then altered the conditions that allowed the plant to thrive. This doesn't mean the system was aiming for a particular outcome. There's no intention or goal involved. But it does illustrate how feedbacks between life and the environment can create patterns that look, from a distance, like regulation. At the same time, the event also shows the limits of this idea. The cooling did not stop at some perfect, stable point. The planet continued to evolve, eventually moving into much colder states. Life adapted to those states, but many species were also lost along the way. The system didn't preserve everything, it changed. From a modern perspective, this can be a sobering thought. Earth's climate has always been dynamic. Stability, in the sense of a single, unchanging state, is not the norm over geological time. What is more common is a sequence of different states, each lasting long enough for life to adapt, but each eventually giving way to another. The Azolla Event marks one of those transitions. There is also a lesson about uncertainty and complexity. Even with all the evidence scientists have gathered, the exact role of Azolla in the global cooling of the Eocene is still debated. Some researchers emphasize its importance. Others point to tectonic changes, volcanic activity, and the opening and closing of ocean gateways as equally or more significant. This reflects the reality that climate change, past or present, rarely has a single cause. It's usually the result of multiple influences acting together. Recognizing this complexity doesn't weaken the story, it strengthens it. It shows that Earth's climate is shaped by a web of interactions, not by a simple chain of events. The Azolla Event is one thread in that web, and a particularly interesting one because it highlights the role of biology in what is often thought of as a purely physical system. Another insight comes from the way the event connects different parts of the planet. A process that took place in a remote polar basin influenced the composition of the atmosphere. The atmosphere, in turn, influenced climates across the globe. This kind of connection is a reminder that Earth doesn't operate in isolated compartments. The ocean is connected to the air is connected to the land is connected to the ocean. Changes in one part of the system can propagate through the whole. This interconnectedness is one of the reasons climate science is such a challenging field. To understand what's happening in one place, you often have to look at processes happening far away or even deep beneath the surface. The Azolla Event also offers a way to think about resilience. The planet did not collapse or break under the changes it experienced. It adjusted. Ecosystems shifted. New species emerged. Others disappeared. The system found new ways to operate under new conditions. This doesn't mean change is harmless. From the perspective of individual species or ecosystems, climate shifts can be profoundly disruptive. But on the scale of the planet as a whole, change is part of the ongoing story. The floating fern, in this sense, became part of a much larger narrative of adaptation and transformation. There's also a lesson in humility here. Humans often see themselves as the primary drivers of environmental change, and in the modern era, that's increasingly true in many respects. But Earth's history is full of examples where non-human life has had a profound impact on the planet's physical state. The rise of oxygen in the atmosphere, driven by early photosynthetic microbes, transformed the planet and reshaped the course of evolution. The formation of large forests in the Carboniferous period influenced carbon storage and climate. The Azolla Event is another chapter in this long history of life shaping the world it inhabits. Understanding these past events can broaden our perspective on what is possible within Earth's system, and on the range of outcomes that can arise from relatively simple biological processes. At the same time, the Azolla Event reminds us of the difference between what is possible and what is practical. The carbon removal associated with the floating fern took place over immense spans of time and under very specific conditions. It was not a quick fix. It was a slow, cumulative process. This doesn't diminish its importance. It just places it in the proper context of geological time rather than human time. As we reflect on what this ancient episode teaches, it can be useful to hold two ideas in mind at once. First, that small, persistent processes can lead to very large outcomes. Second, that the pace of those processes matters just as much as their direction. The Azolla Event changed the climate by steadily removing carbon from the atmosphere over a long period. The modern world is changing the climate by adding carbon to the atmosphere over a much shorter period. The underlying system, the flow of carbon between air, water, life, and rock, is the same. The speed and direction of the flow are different. This contrast can help clarify why climate change today feels so disruptive. The planet's systems are being asked to adjust on a timescale that is much shorter than the one they experienced during events like the Azolla period. That doesn't mean the past provides a simple blueprint for the future, but it does offer a deeper understanding of the mechanisms at work. Let the lesson of climate power settle in, not as a tale of dominance or control, but as a reminder of connection and accumulation. A leaf floats, A leaf sinks. A molecule of carbon moves from sky to water to stone. The repetition of that simple sequence, spread across a vast area and an immense span of time, becomes part of a force strong enough to nudge a planet into a new state. It's a kind of power that doesn't shout. It doesn't rush. It works quietly, patiently, and almost invisibly, shaping the world not through a single act, but through the steady rhythm of countless small ones, layered on top of each other until, one day, the outcome is written into the climate itself. Long before humans began to measure time with calendars and clocks, long before forests took on familiar shapes and oceans settled into the patterns we recognize today, the planet was already being guided by lives so small they would have slipped through the spaces between our fingers without leaving a trace. These lives did not move mountains in a literal sense. They did something quieter, and over time, just as profound. They changed the chemistry of the air, the colour of the seas, and the direction of the planet's long, slow journey through warmth and cold. The Azolla Event is one chapter in that much larger story, a reminder that Earth's history is not written only by the largest creatures or the most dramatic forces. It's also shaped by microbes, algae, and tiny plants that work on a scale almost too small to imagine, yet do so in numbers and over durations that give them a kind of collective weight. To appreciate this, it helps to step even further back in time, beyond the warm Arctic seas and floating ferns, to a world that looked almost nothing like the one we know. Billions of years ago, the atmosphere of Earth held very little oxygen. The sky would not have been blue in the way it is now. The oceans were filled with dissolved metals, and the land, where it existed above water, was barren and rocky. Life, at least the kind that could survive in such conditions, was mostly microscopic. Among those early forms of life were organisms that discovered a powerful trick. They learned how to use sunlight to split water molecules and fix carbon dioxide into organic matter, releasing oxygen as a byproduct. These were the ancestors of modern cyanobacteria, the same general group of microbes that would one day partner with Azolla inside its leaves. At first, the oxygen they released didn't accumulate in the atmosphere. It reacted with metals in the ocean and rocks on land, forming oxides and sinking out of sight. But as more and more of these microbes spread across the planet's surface waters, the supply of oxygen began to overwhelm these sinks. Eventually, oxygen started to build up in the air. This event, often called the Great Oxidation Event, transformed the planet. It made the atmosphere breathable for organisms that rely on oxygen to generate energy efficiently. It also made the environment hostile for many forms of life that had thrived in low oxygen conditions, driving widespread extinctions. At the same time, the presence of oxygen in the atmosphere allowed for the formation of an ozone layer, which protects the surface from harmful ultraviolet radiation. This opened the door for life to move out of the oceans and onto land. All of this came from the collective activity of tiny single-celled organisms. In this context, the Azolla Event begins to feel less like an isolated curiosity and more like part of a long tradition. Again and again, small life has found ways to influence the planet at a scale far beyond what its individual members could ever achieve alone. Another example lies in the formation of limestone and other carbonate rocks that make up vast portions of the Earth's crust. These rocks are largely built from the shells and skeletons of microscopic marine organisms, such as foraminifera and coccolithophores. These tiny creatures live near the surface of the ocean, where they use dissolved carbon and calcium to build protective structures. When they die, those structures sink to the seafloor and accumulate as sediment. Over time, pressure and chemical changes turn that sediment into solid rock. This process locks away enormous amounts of carbon in mineral form. It is one of the main reasons the Earth's atmosphere does not contain far more carbon dioxide than it does. If you were to look at a cliff of chalk or limestone today, you would be looking at the compressed remains of countless microscopic organisms layered over millions of years, a solid, towering formation built from the quiet work of tiny lives. The Azolla Event fits into this same pattern, but with a twist. Instead of building carbon into rock through mineral shells, Azolla and its microbial partners built it into organic matter that was then buried and transformed by the processes of sedimentation and pressure. Both pathways move carbon from the fast surface-level system into the slow geological one. Both rely on the steady accumulation of small contributions over long spans of time. There is also the story of the Carboniferous period, a time around 300 million years ago when vast swamp forests covered much of the land. These forests were dominated by towering plants and trees, but at their base, in the waterlogged soils, microbial activity was just as important. The conditions in those swamps slowed the decay of plant material. Dead trees and leaves accumulated in thick layers of peat, which were later buried and transformed into coal. This process removed large amounts of carbon from the atmosphere, contributing to a period of global cooling and the formation of ice at the poles. Once again, life and climate were linked through the movement of carbon from air to plant to sediment. The difference in the Azolla case is that this entire sequence played out on the surface of an ocean, in a place that, for much of Earth's history, has been seen as a boundary rather than a stage. The floating ferns turned the Arctic Ocean into something more like a shallow, sprawling wetland, blurring the line between land and sea. These examples point to a broader principle. The Earth's climate is not just controlled by physical forces like sunlight, gravity, and the movement of tectonic plates. It is also shaped by the collective behaviour of living things. This does not mean that life is in charge of the planet in any simple sense. Physical processes still set the broad boundaries. The amount of energy the Earth receives from the Sun, the arrangement of the continents, and the chemistry of the rocks all play crucial roles. But within those boundaries, life can steer the system in different directions, sometimes in subtle ways, sometimes in ways that leave marks visible millions of years later. One of the reasons tiny organisms are so effective at this is their sheer numbers. A single bacterium or plankton cell is almost weightless, but the oceans and soils contain unimaginable quantities of them. A teaspoon of seawater can hold millions of microorganisms. A handful of soil can contain more living cells than there are humans on the planet. Each one of those cells is carrying out chemical reactions. Each one is moving atoms around, turning gases into solids, solids into gases, one molecule at a time. When you multiply that by trillions upon trillions, and then let it run for thousands or millions of years, the cumulative effect becomes planetary. Another factor is their speed of reproduction. Tiny organisms often have very short life cycles. They can multiply, adapt, and evolve quickly. This allows them to respond rapidly to changes in their environment, taking advantage of new conditions and spreading into new niches. In the case of Azolla, this meant that once the right combination of light, fresh water, and nutrients appeared in the Arctic, the fern could expand quickly, covering large areas in a relatively short geological time. Microbes show this adaptability even more strongly. They can evolve new metabolic pathways, allowing them to use different chemical reactions to obtain energy and build their cells. Over Earth's history, microbes have discovered ways to use sulfur, iron, methane, and other substances as part of their metabolism, influencing the chemical composition of the environments they inhabit. These microbial processes can shape everything from the acidity of the oceans to the composition of the atmosphere. There is also an interesting relationship between tiny organisms and the planet's physical structure. In some cases, microbes and small plants can influence the formation of minerals and rocks. For example, certain bacteria can induce the precipitation of calcium carbonate, contributing to the formation of limestone. Others can dissolve minerals, accelerating the weathering of rocks and the release of nutrients and carbon. These interactions blur the line between the living and the non-living. Rocks influence life by providing nutrients and surfaces to grow on. Life influences rocks by changing their chemistry and structure. The Azolla Event sits at this boundary. A living plant altered the chemistry of the air and water. The resulting changes influence the formation of sediments and eventually rocks. Another reason tiny organisms have such an outsized role is their position at the base of most food webs. In the ocean, microscopic plankton capture energy from sunlight and form the foundation for nearly all marine life. Fish, whales and seabirds ultimately depend on the productivity of these tiny cells. When plankton communities change, the effects can cascade through the entire ecosystem. This can influence not just who eats whom, but also how much organic material is produced and how much of it sinks to the sea floor. In this way, the structure of a microscopic community can influence the flow of carbon on a global scale. On land, soil microbes play a similar role. They break down dead plant material, releasing nutrients that new plants need to grow. They also control how much carbon is stored in the soil and how much is released back into the atmosphere. Soils are one of the largest reservoirs of carbon on the planet, holding more than the atmosphere and all living plants combined. The activity of tiny organisms in the soil determines whether that carbon stays put or returns to the air. This perspective can make the Azolla Event feel less like a strange anomaly and more like a particularly visible example of a general pattern. Life at small scales is constantly shaping the planet's chemistry, and through that chemistry, its climate. There is also a temporal dimension to this influence. Tiny organisms often operate on short timescales, but their effects can persist long after the organisms themselves are gone. The oxygen produced by ancient cyanobacteria continues to fill the atmosphere billions of years later. The limestone built from microscopic shells still forms cliffs and mountains. The organic rich sediments from the Azolla period remain buried beneath the Arctic seafloor. This creates a kind of delayed impact. The actions of small life in the past continue to influence the conditions for life in the present and future. From a scientific standpoint, this makes the study of ancient microorganisms and plants especially valuable. By understanding what they did and how they interacted with their environment, researchers can gain insight into how the Earth system might respond to changes in the present. This is not about drawing simple, direct comparisons. The conditions of the Eocene Arctic are not the same as those of the modern world. The timescales are different. The configuration of continents and oceans is different. The types of organisms involved are different. But the underlying processes, the movement of carbon, the flow of energy, the feedbacks between life and environment remain fundamentally similar. Another aspect of the outsized role of tiny organisms is how they can create thresholds and tipping points. Because they often respond quickly to environmental changes, they can amplify those changes under the right conditions. For example, a slight increase in temperature might allow a certain type of plankton to grow more rapidly. That growth could draw down more carbon dioxide, leading to cooling, or it could alter the reflectivity of the ocean's surface, affecting how much sunlight is absorbed. In other cases, microbial activity can release greenhouse gases like methane from sediments or wetlands, contributing to warming. These feedbacks can push the system toward new states. Once a threshold is crossed, the system may not easily return to its previous condition. The Azolla Event appears to have been part of such a transition. The growth of floating ferns and the burial of their carbon contributed to a shift away from a greenhouse world toward a cooler climate regime. This doesn't mean Azolla alone caused that shift, but it suggests that biological processes played a role in pushing the system across a threshold that physical processes alone might not have crossed as quickly or as smoothly. There is also a lesson here about the visibility of influence. We tend to notice the impact of large animals, large storms, and large geological events. We don't often notice the impact of bacteria or tiny plants. Yet, in the long run, those small forms of life may have left deeper marks on the planet's history than many of the things we consider dramatic. The very air we breathe is a product of microbial activity in the deep past. The rocks beneath our feet are often built from the remains of microscopic organisms. The composition of the oceans and the distribution of nutrients within them are shaped by the ongoing work of plankton and bacteria. In this sense, Earth can be seen as a planet that has been co-created by its smallest inhabitants. The Azolla Event also invites reflection on how interconnected the world is across scales. A change in the growth of a tiny plant in a remote polar basin influenced the composition of the atmosphere. That change in the atmosphere influenced global temperatures. Those temperatures influenced ecosystems on land and in the sea across the planet. This chain of connections challenges the idea that small and large, local and global are separate categories. On Earth, they are often linked in ways that only become apparent when you look across long spans of time. There's a quiet elegance in that. The same processes that allow a leaf to grow on the surface of a pond can, under the right conditions, become part of a system that shapes the climate of an entire world. From a human perspective, this can inspire both awe and caution. Awe, because it highlights the complexity and subtlety of the planet we live on. Caution, because it shows how sensitive that planet can be to changes in the flow of key elements like carbon. The story of tiny organisms shaping Earth's history is not just a story of the distant past. It continues today. Every day, plankton in the oceans capture carbon from the air. Soil microbes break down organic matter. Wetlands release methane. Forests store carbon in wood and soil. Coral reefs build limestone structures from dissolved minerals. All of these processes are part of the same grand exchange between life and the planet's physical environment. The difference is that now humans are also a major participant in that exchange. By moving large amounts of carbon from long-term storage and fossil fuels into the atmosphere, we're altering the balance that tiny organisms and geological processes have maintained over long periods. In this context, the Azolla Event can serve as a kind of mirror. It shows what happens when carbon flows steadily in one direction, from air to rock, driven by biological processes. It invites us to think about what it means to push that flow in the opposite direction. Again, the comparison is not perfect. The timescales and conditions are different, but the underlying system is the same. Another point worth considering is how much of Earth's history is still hidden from view. The discovery of the Azolla layers was relatively recent, made possible by technology and international cooperation that didn't exist before. There may be other chapters of the planet's story, driven by small organisms and subtle processes that remain buried in sediments or rocks, waiting to be uncovered. Each new discovery adds to the sense that Earth's history is more complex and more interconnected than we often assume. As you let this idea settle, it can be helpful to return to a simple image. A tiny, floating fern on the surface of a calm, ancient sea. Inside its leaves, microscopic partners fixing nitrogen. Sunlight pouring down from a sky that barely darkens. On its own, that scene feels small and quiet. But when you connect it to the layers of sediment below, the chemistry of the air above, and the long arc of the planet's climate, it becomes part of something vast. The outsized role of tiny organisms is not about heroics or intention. It's about accumulation, about the way countless small actions, repeated over and over again, can add up to something that reshapes the world. The smallest lives, moving the largest systems, the quiet work of leaves and microbes, written into stone, air, and ocean across millions of years. It's a reminder that on this planet, influence doesn't always announce itself. Sometimes it drifts, grows, sinks, and settles, and only much later do we realize just how far its reach has gone. Across the long sweep of Earth's history, the idea of a single event repeating itself in the same way is almost always an illusion. The planet changes its shape, its chemistry, and its living communities so thoroughly over time that even when similar processes appear, they unfold in different settings, under different rules, and with different outcomes. So when we ask whether something like the Azolla event could happen again, we're really asking a deeper question about how flexible, how responsive, and how constrained the Earth system truly is. To begin exploring that, it helps to step away from the image of a specific plant in a specific place, and instead look at the broader ingredients that made the Azolla story possible. There was a semi-enclosed ocean basin. There was a steady supply of fresh water and nutrients from surrounding land. There was a long growing season with abundant sunlight. There was a biological pathway that allowed carbon to be captured efficiently at the surface and buried effectively in low oxygen sediments below. None of those elements on their own are unique. What made the Azolla Event stand out was how they aligned in one place for a long enough time to matter on a planetary scale. If we scan the modern world for similar alignments, we can find pieces of the puzzle, but rarely the whole picture. Take freshwater input, for example. Today, large rivers still pour enormous volumes of fresh water into the ocean. The Amazon, the Congo, the Ganges, and many others create surface layers of relatively fresh water that can extend far offshore. In some regions, these plumes can influence local ecosystems, supporting blooms of plankton and altering the chemistry of the surface ocean. But most modern ocean basins are far more open and connected than the ancient Arctic was. Strong currents and winds mix surface and deep waters more thoroughly, making it harder for a stable, long-lived freshwater layer to persist over vast areas. Then there's sunlight. High-latitude regions still experience long summer days just as they did in the Eocene. The sun still circles the sky near the poles, offering extended periods of light. But the temperature conditions are very different. Modern polar oceans are much colder, and ice cover, even when seasonal, can limit how much light reaches the water. This changes the character of surface ecosystems. Instead of floating plants like Azolla, which prefer warmer, fresher conditions, modern polar seas are dominated by microscopic algae that can grow in cold, salty water and even within the ice itself. Nutrients too still play their role. Upwelling currents in certain parts of the ocean bring nutrient-rich deep water to the surface, fueling massive blooms of phytoplankton. These blooms can cover large areas and produce enormous amounts of organic matter. In some respects, these plankton blooms are modern cousins of the Azolla mats. They capture carbon through photosynthesis. When the organisms die, some of that carbon sinks toward the seafloor. This process is known as the biological pump, and it is one of the main ways the ocean removes carbon from the atmosphere today. So in terms of basic mechanisms, the Earth still has the ability to move carbon from air to life to sediment. That pathway never disappeared. What has changed are the details of how efficiently and where it operates. One of the key differences between the Azolla Event and the modern ocean lies in the fate of sinking organic matter. In many parts of today's seas, the deep waters are well oxygenated. As organic material sinks, it is often consumed and broken down before it can be buried in sediment. This means that much of the carbon captured at the surface eventually returns to the water and the atmosphere, completing a relatively short cycle. There are exceptions. In certain regions, such as oxygen-poor zones off the coasts of some continents, organic-rich sediments can accumulate and preserve carbon more effectively. These areas, sometimes called dead zones, can act as localized sinks for organic material, but they are generally limited in extent and often associated with complex and sometimes fragile ecological conditions. Another major difference is the scale of the modern ocean. The ancient Arctic basin, with its partial enclosure and limited circulation, was particularly well suited to preserving a stable surface layer and low oxygen depths. Most of today's oceans are more dynamically connected, with global circulation patterns that move water and dissolved gases around the planet. This circulation makes it harder for any one region to become a dominant, long-term carbon sink in the way the Arctic basin did during the Azolla period. That doesn't mean the ocean is not important in regulating carbon today. It absorbs a significant fraction of the carbon dioxide humans release into the atmosphere. But much of that carbon remains in the surface and intermediate waters for centuries, rather than being locked away in sediments for millions of years. There is also the matter of biology. Azolla is a freshwater plant with a very specific set of needs and advantages. its ability to fix nitrogen internally gave it an edge in nutrient-limited environments. Its floating lifestyle kept it in the light. In the modern ocean, most of the heavy lifting is done by microscopic phytoplankton rather than by visible floating plants. These organisms come in many forms, from diatoms with glassy shells to tiny cyanobacteria that drift with the currents. Some of these microbes also fix nitrogen, playing a role similar to Azolla's bacterial partners. They can thrive in low-nutrient environments and contribute significantly to marine productivity. But their small size and different life cycles mean that the way their organic matter sinks and is processed can be quite different. Much of it is broken down in the water column rather than reaching the seafloor intact. If we look beyond the oceans, there are also land-based processes that echo parts of the Azolla story. Forests, wetlands and peatlands can act as long-term carbon sinks under the right conditions. In waterlogged soils, where oxygen is limited, plant material can accumulate and form peat. Over very long periods, this peat can be buried and transformed into coal, much as it was during the Carboniferous period. Modern peatlands store enormous amounts of carbon, especially in the high-latitude regions. They cover only a small fraction of the Earth's land surface, but they hold a disproportionate share of the planet's soil carbon. In this sense, there are places on land today that function, in a loose way, like the ancient Arctic basin did for Azolla. They provide conditions where organic matter can accumulate and be preserved. However, these systems are also sensitive to changes in temperature and water balance. If they dry out or warm significantly, the stored carbon can be released back into the atmosphere. This highlights another important aspect of the question. The Azolla Event didn't just require a pathway for carbon burial, it required stability. The conditions that allowed Azolla to thrive and its remains to be preserved had to persist for a very long time. In the modern world, many environments are experiencing rapid change. Climate shifts, land use and human activities alter water flows, temperatures and nutrient cycles on timescales of decades rather than millennia. This makes it harder for slow, cumulative processes like long-term carbon burial to operate in the same way they did in the deep past. There is also the question of timescale when we talk about happening again. The Azolla Event unfolded over hundreds of thousands to millions of years. From a geological perspective, that's not especially long. From a human perspective, it's almost unimaginably slow. If something like it were to begin today, it would not be noticeable in any direct way for many, many generations. This doesn't mean similar processes aren't happening right now. They are. Every day, plankton capture carbon. Every year, organic matter is buried in sediments. Every decade, soils and wetlands accumulate and release carbon. But whether these processes will add up to a major long-term shift in the planet's climate depends on how they balance against other forces, especially those that move carbon in the opposite direction. In Earth's history, major shifts in atmospheric carbon often coincide with changes in tectonics and geology. The uplift of large mountain ranges can increase the rate of chemical weathering, which draws carbon dioxide out of the atmosphere and locks it into minerals. The opening and closing of ocean gateways can alter circulation patterns, influencing how heat and nutrients are distributed. These large-scale physical changes can create the background conditions that allow biological processes to become more or less influential. In the Eocene, the configuration of continents and oceans helped create a quiet, enclosed Arctic basin. In the modern world, the continents are arranged differently. The Arctic is more open, more connected to the Atlantic and Pacific, and more exposed to global circulation. This makes a direct repeat of the Azolla Event, in the same place and the same form, unlikely. But that doesn't mean the planet has lost the ability to produce large, biologically driven changes. It just means those changes would likely take a different shape. One area of active research looks at regions where large-scale blooms of phytoplankton occur, such as parts of the Southern Ocean. This ocean surrounds Antarctica and plays a major role in the global carbon cycle. Cold, deep waters rise to the surface there, bringing nutrients that can fuel productivity. Some scientists study how changes in iron availability, which can limit plankton growth in these waters, might influence the ocean's ability to absorb carbon dioxide. The idea is that small changes in nutrient supply can have outsized effects on biological activity and, by extension, on carbon flow. Another area of interest is the Arctic itself, which is once again undergoing rapid change, though in a very different direction from the one we've been discussing. Modern Arctic warming is reducing ice cover, increasing the amount of open water and sunlight available in summer. This can lead to increased biological productivity in some regions, including larger blooms of phytoplankton. In a limited sense, this creates a parallel to the ancient story. More open water and more light can support more growth. More growth can capture more carbon. But the modern Arctic also has stronger mixing, different circulation patterns, and a very different chemical environment. Much of the organic matter produced at the surface is still likely to be recycled rather than buried. There is also a deeper, more philosophical layer to the question of repetition. Earth's history is not a loop that simply runs through the same events again and again. It's more like a branching path, where each state of the planet sets the conditions for what can come next. The Azolla Event happened in a world that had no permanent polar ice, different continental positions, and a different baseline climate. The modern world has permanent ice sheets, different ocean gateways, and a different atmospheric composition. These differences matter. They shape what kinds of processes can become dominant and how effective they can be. Still, the broader lesson of the Azolla Event remains relevant. It shows that under the right conditions, biological processes can influence the global carbon cycle in meaningful ways. That idea has inspired research into how ecosystems might be supported or restored in ways that enhance their natural ability to store carbon. Forests, wetlands, mangroves, seagrass meadows and peatlands are all examples of systems that can act as carbon sinks when they are healthy and stable. These modern ecosystems are not direct analogues of the Azolla mats, but they share a common theme. They rely on the growth of living organisms and the preservation of organic matter to move carbon from the atmosphere into longer-term storage. There is also a growing interest in understanding how microbial communities in soils and sediments influence carbon storage. These tiny organisms determine whether organic matter is broken down and released or transformed and preserved. In a way, this brings the story back to the smaller scales. Even today, much of the planet's ability to store or release carbon depends on the activity of microbes we cannot see. Another point to consider is the role of chance and contingency. The Azolla Event required a specific alignment of factors. A different continental arrangement, a slightly different climate, or a different set of species might have led to a very different outcome. This suggests that while Earth has general tendencies and feedbacks, it is also shaped by particular histories. The path it takes is not entirely predetermined. From this perspective, asking whether something like the Azolla Event could happen again is less about predicting a specific future and more about understanding the range of possibilities the Earth system contains. The planet has demonstrated that it can move large amounts of carbon between its surface and its deep reservoirs. It has done so through a variety of pathways, some driven by geology, some by biology, and often by a combination of both. The question is not so much whether it can happen again, but under what conditions and in what form. If, at some point in the far future, the continents rearrange themselves into a configuration that creates another semi-enclosed, nutrient-rich, stable basin at high latitude, and if the climate provides long growing seasons and warm surface waters, then it's not impossible to imagine another biological system taking on a role similar to Azolla's. It might not be a fern, it might be a different kind of plant or a microbial community with a different set of abilities, but the underlying principle, that life can become part of a major carbon pathway, would still apply. At the same time, it's worth remembering how rare and fleeting such alignments can be. The Azolla Event was a product of a particular moment in Earth's long history. It lasted long enough to matter, but it did not last forever. from the standpoint of the planet's 4.5 billion year story, it was a chapter, not a permanent state. As you sit with this question, it can be helpful to let go of the idea of exact repetition. Instead, think in terms of patterns. The pattern of life interacting with environment, the pattern of carbon moving between air, water and rock, the pattern of feedbacks that can amplify or limit change. Those patterns are still very much alive today. The oceans continue to absorb and release carbon. Plants on land continue to grow and decay. Sediments continue to accumulate at the bottom of seas and lakes. Microbes continue to work, molecule by molecule, shaping the chemistry of their surroundings. All of these processes are part of the same Earth system that once allowed a floating fern to influence the climate of a warm, ancient world. If something like the Azolla Event were to happen again, it would not look the same. It would emerge from a different set of conditions, involve different organisms, and unfold in a world shaped by a different history. But the deeper lesson, that small, persistent biological processes can become part of large, planetary changes, would remain. For now, let the question itself linger rather than settle into a simple answer. The planet is not a machine that repeats the same cycle over and over. It's a system that evolves, responds, and sometimes surprises. In that sense, the most honest response to whether something like this could happen again is not a confident yes or no, but an invitation to keep watching, keep learning, and keep paying attention to the quiet, often unseen processes that continue to shape the world beneath our feet and the sky above our heads. In the quiet spaces where layers settle and time seems to slow to a near standstill, the planet keeps a kind of record that doesn't rely on words, ink, or memory in the human sense. It writes its history in particles that fall through water, in crystals that grow inside ice, and in minerals that lock together under pressure. Long after voices fade and landscapes shift, these materials remain, holding on to traces of what the world once was. To understand this idea of Earth's memory, it helps to think about how information can be stored without anyone intending to store it. When a leaf falls into a lake, it doesn't mean to become a data point. When snow settles on a glacier, it doesn't plan to carry a message. Yet, in the right conditions, both can become part of a long-term archive. Mud is one of the most reliable of these accidental record keepers. In lakes, seas, and oceans, fine particles drift down from above or wash in from the land. Some are grains of mineral eroded from distant mountains. Others are fragments of shells, bits of organic matter, or tiny crystals that form directly in the water. Together they settle into thin layers on the bottom. Each layer reflects something about the conditions at the time it was formed. The size of the particles can hint at how fast the water was moving. The types of minerals can suggest where the material came from. The presence of certain organic compounds can point to the kinds of life that were active in the water above. Over years, these layers stack up. Over centuries, they compress. Over thousands and millions of years, they turn into sedimentary rock. What began as a soft, shifting surface becomes a solid, structured archive. In the case of the Azolla Event, this process created one of the most striking examples of the planet's memory written in mud. The dark, organic, rich layers beneath the Arctic seafloor are not just collections of particles. They are physical traces of a time when the surface of the ocean was covered in green, when freshwater and sunlight combined to support an ecosystem that no longer exists. Those layers don't tell their story all at once. They have to be read. Scientists approach them the way a historian might approach an ancient manuscript, except instead of ink and parchment, they work with chemical signatures and mineral grains. A change in colour from one layer to the next can signal a shift in the amount of organic matter. A difference in grain size can indicate a change in current strength or sediment source. The ratios of certain elements like carbon, oxygen and nitrogen can reveal information about temperature, productivity, and the balance between fresh water and salt water. Each measurement is like a sentence in a language that has to be learned and interpreted. Ice offers another kind of record. one that is, in some ways, even more delicate. In polar regions and high mountains, snow falls year after year and doesn't completely melt. Instead, it compresses into ice, trapping tiny bubbles of air and particles of dust inside. Those bubbles are samples of the atmosphere at the time the snow fell. They hold the exact mix of gases that were present, including carbon dioxide, methane, and oxygen. By drilling deep into ice sheets and extracting long cores, scientists can travel back through the history of the air itself. Each layer of ice represents a season or a year. In some places, the record goes back hundreds of thousands of years. The deeper you go, the older the ice and the older the air inside it. This makes ice one of the most direct forms of the planet's memory. It doesn't just hint at past conditions, it preserves them. In the context of the Azolla story, ice records from other parts of the world help provide a broader backdrop. While the Arctic itself did not preserve ice from the Eocene period, the later development of ice sheets and glaciers carries forward the story of cooling that began in earlier times. The composition of gases in these ice cores shows how atmospheric carbon dioxide levels changed over time. When compared with sediment records from the ocean, a picture emerges of how carbon moved between air, water, and rock. Stone, the third part of this quiet archive, holds its own kind of memory. Rocks are not static objects. They are the result of processes that can take millions of years, and they often preserve the conditions under which they formed. Sedimentary rocks, in particular, are built from layers of material laid down over time. Sandstone, shale, and limestone all tell stories about the environments in which they originated. A limestone cliff might represent a long-gone shallow sea filled with shell-building organisms. A layer of coal might point to an ancient swamp where plant material accumulated faster than it could decay. In the Arctic region, the rocks beneath the seafloor include layers that were once mud-rich in organic material. Over time, pressure and chemical changes transform that mud into more solid forms, but the signature of its origin remains. These stone records don't just preserve local histories, they can be matched with records from other parts of the world to build a global picture. When similar patterns appear in rocks on different continents, scientists can link them to large-scale events, such as changes in climate, sea level, or the composition of the atmosphere. The idea that the planet remembers in this way can feel almost poetic, but it's grounded in very physical processes. Memory in this sense is simply persistence, a pattern that forms and is not erased. What determines whether a pattern is preserved or lost often comes down to stability. In a fast-moving river, sediment is constantly being eroded and redeposited. Layers don't have time to settle into a lasting structure. In a calm, deep basin, material can accumulate gently and remain undisturbed. The ancient Arctic basin was, for a time, one of those calm places. Its relatively enclosed nature and stable water layers created conditions where organic, rich sediments could build up and stay in place. That stability allowed the memory of the Azolla Event to be written and kept. Not all memories survive. Many layers of sediment are destroyed by erosion, subduction, or metamorphism. Rocks can be melted back into magma. Ice can melt and release its trapped air. The Earth is constantly recycling its own surface. This makes the records that do survive all the more valuable. They are fragments of a much larger story, pieces that happen to avoid being erased. There is also a sense in which the planet's memory is not evenly distributed. Some regions, like deep ocean basins and polar ice sheets, are particularly good at preserving long-term records. Others, like mountain ranges and coastlines, are more likely to lose their past to erosion and tectonic change. This unevenness shapes what we can know about Earth's history. It means that some chapters are detailed and clear, while others are incomplete or missing entirely. The Azolla Event is one of the clearer chapters, at least in terms of having a distinct signature in the sediment record. The thick, dark layers beneath the Arctic seafloor stand out in a way that invites attention and study. But even here, the story's not perfectly complete. Scientists can infer a great deal about what happened, but they can't see every detail. They don't know exactly how dense the floating mats were in every part of the basin, or how quickly conditions change from one phase to another. The memory preserved in mud and stone is rich, but it is also partial. This partiality is part of what makes the work of interpretation so careful and ongoing. New techniques can reveal information that was previously hidden. Advances in chemistry allow for the detection of ever more specific molecular markers. Improvements in imaging can show the fine structure of sediment layers in greater detail. Each new method adds a little more clarity to the picture, sometimes confirming existing ideas, sometimes challenging them. Ice cores, too, continue to provide new insights as drilling reaches deeper and deeper layers. The air trapped inside ancient ice tells stories not just about carbon dioxide, but about volcanic eruptions, wildfires, and even changes in vegetation. Tiny particles of ash from distant eruptions can be found in ice layers, marking specific moments in time. Dust carried by wind can reveal patterns of aridity and wind strength in faraway regions. All of these details contribute to a broader understanding of how the planet's systems have interacted over time. There's a quiet beauty in the way these different forms of memory connect. A change recorded in mud beneath the ocean can be reflected in the composition of air trapped in ice thousands of kilometers away. A shift in the chemistry of a rock layer can align with a change in fossil communities on another continent. These connections highlight the global nature of the Earth system. The planet's memory is not stored in isolated compartments. It's woven together across different materials and places. From a human perspective, this can be both comforting and humbling. Comforting, because it means that the world carries its own history, even when no one is there to witness it. Humbling, because it reminds us that our own records, however detailed, are tiny in comparison to the planet's deep archive. There is also something grounding about the timescales involved. A single layer of sediment might represent a year, a decade, or a century. A stack of layers can represent millions of years. The planet's memory stretches far beyond any human lifetime. This can change the way we think about change itself. What feels fast to us can be slow in geological terms. What feels permanent to us can be fleeting on the scale of rocks and ice. The Azolla Event, for example, lasted long enough to influence the global climate, but it was still a brief episode in the planet's history. The layers that record it are just one part of a much thicker stack that spans hundreds of millions of years. Yet, despite its relative brevity, it left a mark that we can still read. There's also a sense in which the planet's memory is active rather than passive. The records preserved in mud, ice, and stone don't just sit there. They influence what comes next. Sediments can affect how water flows through the ground. Rocks can shape the landscape, guiding rivers and determining where soils form. Ice can reflect sunlight and influence climate. In this way, the past is not just remembered, it becomes part of the present. The organic rich layers beneath the Arctic sea floor, for instance, influence the physical properties of the sediments. They can affect how the seafloor responds to pressure and how fluids move through it. Over very long periods, they can play a role in the formation of hydrocarbon resources. The ice sheets that formed later in Earth's history, influenced in part by long-term cooling trends, continue to shape the planet's climate and sea level today. The memory of past climates preserved in these materials becomes a factor in present conditions. From a scientific standpoint, this interplay between past and present is one of the reasons studying ancient records is so valuable. It helps researchers understand not just what happened, but how the system responds to change. By looking at how carbon levels, temperatures, and ecosystems shifted in the past, scientists can test their models of how the Earth system works. They can see whether the same relationships hold under different conditions. The Azolla Event provides one such test case. It shows a period when biological processes appear to have played a role in drawing down atmospheric carbon and cooling the planet. By examining the details of this process, researchers can refine their understanding of the carbon cycle and its sensitivity to changes in productivity and burial. There is also an educational aspect to the planet's memory. The rocks, sediments and ice we study today are, in a sense, teachers. They offer lessons about resilience, feedbacks, and the long-term consequences of change. They show that the Earth system can shift between different states. They show that life can influence those shifts. They show that stability and change are both part of the planet's nature. For those who work with these records, there is often a feeling of connection to deep time. Holding a piece of sediment that was once part of a warm, ancient sea can feel like touching a moment far removed from the present. This connection can bring a sense of perspective. It places current concerns and experiences within a much larger context. At the same time, it can sharpen awareness of how quickly things can change on human timescales, even when geological records make everything seem slow. The layers that record the last few centuries are thin compared to those that represent millions of years, but the changes within them can be dramatic. This contrast between the thickness of layers and the intensity of change is something scientists pay close attention to when they study recent sediments and ice cores. The idea of memory also invites reflection on what will be preserved from our own time. The materials we produce, the chemicals we release, and the structures we build will become part of the planet's future archive. Plastics, metals, and synthetic compounds are already being found in sediments around the world. They will form a distinct layer in the geological record, a marker of a particular moment in Earth's history. Future researchers, millions of years from now, might read that layer the way we read the Azolla-rich sediments, trying to reconstruct what the world was like and what forces were at work. This thought can feel abstract, but it ties the past, present, and future together in a continuous story. The planet remembers not just what it has been, but what it is becoming. In the context of this long story, the Azolla Event is one memory among many. It sits alongside records of ancient oxygen rises, massive volcanic eruptions, asteroid impacts, and the slow drift of continents. Each of these events left its own signature in mud, ice, and stone. Each one altered the course of the planet in its own way. What makes the Azolla Event stand out is its subtlety. There was no explosion, no sudden catastrophe. There was just growth, sinking, and burial, repeated over and over again. The memory of that repetition is written in dark layers beneath a cold sea. As you imagine that archive, it can be helpful to picture the process in slow motion. A single leaf drifting down through water, a thin film of sediment settling on top of it, another leaf, another film, over and over until the individual leaves are no longer visible, but their combined presence has changed the colour and composition of the layer. That is how the planet writes its memory, not in bold strokes, but in accumulation. There's a quiet comfort in that idea. It suggests that even small, ordinary things can become part of something enduring, given enough time and the right conditions. The floating fern of the Eocene did not know it was becoming part of a geological record. It was simply growing, spreading, and eventually sinking. Yet, through that simple cycle, it contributed to a layer that scientists would one day study to understand the climate of a distant past. In a similar way, the snow that falls today on a glacier, the dust that settles on the ocean floor, and the leaves that fall into a lake are all becoming part of future layers. They are, in their own way, writing the next lines in the planet's memory. Mud holding the remains of a green sea, ice preserving the breath of ancient air, stone carrying the imprint of long-gone worlds, all of it layered, patient and enduring, waiting for those who know how to listen to read the story it has been quietly telling for millions of years. Somewhere between the deep past and the moment you're sitting in right now, the story of Earth folds back on itself in a quiet, almost unnoticed way. The ancient Arctic, with its floating green surface and sinking leaves, is not as far removed from your own world as it might first appear. The same sky arches overhead. The The same oceans move heat and salt and life around the globe. The same basic exchange of carbon between air, water, living things and stone continues, one molecule at a time. What changes is not the system itself, but the pace at which different parts of it take the lead. If you step outside and take a slow breath, the air you draw in carries a mixture of gases that has been shaped by billions of years of living and non-living processes. Oxygen, once rare, now makes up a large part of every inhale. Carbon dioxide, though present in much smaller amounts, plays an outsized role in how warm the planet stays. That invisible balance between gases is part of the same story that once involved a floating fern in a warm polar sea. It can be grounding to think about how ordinary the present moment feels compared to the long layered history beneath it. Streets, buildings, trees and clouds all seem fixed, stable and familiar. Yet, from the perspective of deep time, this moment is just another thin layer settling into place. The ground beneath your feet is likely made of rock that began as sediment in an ancient ocean or riverbed. The soil that supports plants and crops is a mix of mineral grains and organic matter built up over thousands of years. Even the materials in the walls around you, whether stone, metal or glass, come from geological processes that span vast stretches of time. In that sense, the past is not behind you. It is under you, around you, and within the very materials of the world you move through. The Azolla Event, for all its distance in time, is part of this same foundation. The carbon that was buried in Arctic sediments helped shape the planet's climate trajectory. That trajectory influenced where ice formed, how sea levels changed, and how ecosystems evolved. Those changes in turn influenced the distribution of species, the formation of landscapes, and eventually the environments in which humans would appear. This chain of connections can feel abstract, but it becomes more tangible when you consider how closely your own life is tied to the planet's systems. The food you eat depends on plants that capture carbon from the air. The water you drink has cycled through clouds, rivers and soils, shaped by the contours of land and the movement of heat in the atmosphere. Even the energy you use, whether it comes from sunlight, wind or fossil fuels, is part of the planet's long story of carbon and energy exchange. Fossil fuels, in particular, are a direct link to ancient biological processes. They are made from the compressed remains of plants and microorganisms that lived hundreds of millions of years ago, in environments not unlike, in principle, the Azolla-covered Arctic. Burning them releases carbon that was once part of a living system, then locked away in rock. It sends that carbon back into the air, rejoining the fast cycle of atmosphere, ocean and life. This movement, from deep storage back to the surface system, is a reversal of the process that helped cool the planet during the Azolla period. The direction of the flow has changed, even though the pathways remain the same. Thinking about it this way can make the present feel like a crossroads in a much longer journey. The planet has experienced times when carbon moved steadily from air to rock, and times when it moved from rock back to air. Each direction came with its own set of climate conditions and ecological responses. The difference now is the speed. Where ancient processes often unfolded over hundreds of thousands or millions of years, modern changes are happening over decades and centuries. From the perspective of a human lifetime, that can feel gradual. From the perspective of geological systems, it is rapid. This contrast can be hard to hold in mind. On one hand, the planet's history teaches patience. It shows that Earth can absorb, respond to, and recover from profound changes. On the other hand, it also shows that the path from one state to another can involve periods of instability and disruption. The Azolla Event was not a smooth, perfectly controlled transition. It involved shifts in ecosystems, changes in ocean circulation, and the gradual loss of a once dominant floating plant community. The cooling that followed reshaped environments in ways that would have been challenging for many species. The difference was that those species had time, measured in thousands of generations, to respond. In the present, many living systems are being asked to adjust on much shorter timescales. This doesn't mean the planet itself is fragile in a simple sense. Earth has been through ice ages, greenhouse phases, mass extinctions, and long periods of relative calm. It has continued to change and evolve. But it does mean that the particular arrangement of ecosystems and climates that humans depend on is sensitive to the pace of change. There's a subtle shift that can happen when you think about the planet in this long view. Instead of seeing nature as a backdrop for human activity, it starts to look more like a partner in an ongoing process. The forests, oceans, soils and atmosphere are not just resources or settings. They're active parts of a system that has been shaping and reshaping itself for billions of years. Humans are now one of the influences within that system, alongside microbes, plants, tectonic plates and solar energy. This perspective doesn't come with a simple instruction manual. It doesn't tell you exactly what to do, but it can change how you frame questions about the present. For example, instead of asking only how to maintain things as they are, you might also ask how to guide change in ways that allow living systems to continue functioning and adapting. Instead of seeing climate as something external, you might see it as something that emerges from the combined actions of air, water, rock, and life, including human life. There is also a quieter, more personal dimension to this way of thinking. When you realise that the air you breathe has passed through countless lungs, leaves and oceans over millions of years, it can make the act of breathing feel slightly different. The carbon in your own body, in your muscles and bones and skin, was once part of the atmosphere, or the ocean, or a plant. It has been through many forms before becoming part of you, and it will take many forms after it leaves. In that sense, you're not separate from the planet's story. You're one of its temporary expressions. The Azolla Event can serve as a reminder of how even small, ordinary actions, when repeated across large scales and long times, can become part of something much larger. A leaf grows, a leaf sinks, carbon moves. Over time, a climate shifts. In your own life, most actions don't feel like they have planetary consequences. They feel local, immediate, and small, and in many ways they are. But when you multiply small actions across billions of people and many years, they can begin to influence the same kinds of systems that floating ferns and microscopic plankton once did. This doesn't mean every individual action carries equal weight. Systems are complex, and not all influences are the same. But it does suggest that the collective patterns of human activity matter, in the same way that the collective growth of Azolla mattered. There's also something to be said for the role of attention itself. The fact that you can sit, listen, and think about an ancient climate event in a quiet moment is part of a much more recent chapter in Earth's history. For most of the planet's existence, there was no one to wonder about what had come before. Rocks formed, plants grew, oceans shifted, and no one asked why. The emergence of beings capable of curiosity adds a new layer to the planet's story. The Earth doesn't just change, it becomes something that can be studied, remembered, and reflected upon. This capacity for reflection can be seen as another kind of feedback loop. The more we learn about how the planet works, the more we can choose how to interact with it. Those choices then become part of the system's ongoing evolution. The Azolla Event was discovered because people decided to push ships through ice, drill into the sea floor, and analyze tiny molecules in ancient mud. That decision, in turn, shapes how we understand the present and think about the future. There is a gentle irony in that. A story about a plant that changed the planet without intending to end up influencing a species that can intend, plan, and reflect. This doesn't mean humans are suddenly in control of Earth's climate in a complete or absolute way. The system is too large, too complex, and too influenced by forces beyond any single species. Solar energy, tectonic movement, and the chemistry of rock still set the broad stage. But it does mean that human activity has become one of the factors the system responds to, in the same way it once responded to the spread of floating ferns, or the rise of early oxygen-producing microbes. Thinking about this can bring up a range of feelings, from concern to responsibility to curiosity. There's no single, correct emotional response. What can be helpful is to hold on to the sense of connection, the idea that you are part of a system that spans from the smallest microbes to the largest ocean currents, from the deepest sediments to the highest clouds. The Azolla Event becomes, in this light, less of a distant scientific curiosity and more of a reminder of how intertwined life and planet really are. You can also think about the present as another layer being written into the planet's memory. The sediments forming in oceans and lakes today will, over time, become rock. The ice accumulating in glaciers will trap air from this moment. The soils building up in forests and fields will store traces of modern ecosystems. Future scientists, if there are any, might drill into those layers and find evidence of a world that burned fossil fuels, built cities, and altered the chemistry of the atmosphere. They might read those layers the way we read the Azolla-rich sediments, trying to piece together what happened and why. That thought can feel distant, but it places the present in a broader frame. The world you experience now is not just a moment. It is a contribution to a record that will persist long after the details of daily life are forgotten. There is also a quieter, more immediate way to connect with this idea. The next time you notice a plant growing through a crack in the pavement, or algae blooming on the surface of a pond, you can see it as part of the same long story. Photosynthesis is happening. Carbon is moving. Energy from the sun is being turned into living tissue. Some of that tissue will eventually become part of the soil or the sediment at the bottom of a body of water. Most of the time, this cycle doesn't change the world in dramatic ways. It just keeps things going. But under the right conditions, as the Azolla Event shows, it can become something larger. This perspective can make the ordinary feel quietly meaningful. A leaf falling into a stream is not just a leaf falling into a stream. It is part of a process that has been shaping the planet for billions of years. At the same time, it can make the dramatic feel less overwhelming. Climate shifts, geological changes, and ecological transformations are not new. They are part of the planet's long pattern. What is new is the particular role humans now play within that pattern. There's no simple conclusion to draw from this. The story doesn't wrap itself up neatly. The Earth doesn't offer a final chapter. Instead, it continues, layer by layer. The Azolla Event ends, the Arctic cools, ice forms, continents drift, species evolve, and eventually humans appear and begin to ask questions about how it all happened. Now, you are part of that ongoing process, not just as an observer, but as a participant. As this journey drifts back to the present, it doesn't land on a single message or a single lesson. It leaves you with a sense of scale, of connection, and of continuity. The floating fern of a warm ancient sea and the world you inhabit today are linked by the same basic exchanges of matter and energy. The same sunlight drives growth. The same gravity pulls particles down. The same chemistry moves carbon between air, water, life, and rock. The details change, the shapes of continents change, the species involved change. But the underlying conversation between the planet and its living systems continues. If you imagine the Earth as a long story rather than a static place, the present moment becomes a sentence in the middle of a very long page. It is influenced by what came before, and it will influence what comes after. You don't have to solve the whole story. You don't have to know where it's going. You can simply notice that you are here, now, breathing air shaped by ancient plants, standing on ground built from ancient seas, under a sky that has seen worlds warmer and colder than this one. In that awareness, there is a quiet kind of connection, a sense of being part of something that extends far beyond any single moment. And as the planet continues to write its memory in mud, ice, and stone, it also writes it in living things, in forests and oceans, in microbes and animals, and, in its own way, in you. The story does not end here. It doesn't close a door or draw a line. It simply moves forward, carrying the past with it, layer by layer, breath by breath, into whatever comes next.